Hello, 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 hello. Good evening, everyone. Good evening. Can you confirm my voice is audible to you? Can you confirm the voice is audible? Yes, right. Okay. We'll start class in 1 minute at 5:30 exactly, and we'll start with the doubts or homework questions which I gave you yesterday. Okay. So there were 2 homework questions. This was the first homework question, and this was the second homework question. By the time we start clearing it, voice is not clear. One of the student is saying that is because of the fan is running on. I will switch it off when the actual class starts. Okay, so what you have to do by that time is you post your answer and give explanation. That is more important. Give explanation whatever you say here, 0p. Okay, so you give me the explanation why you think that is correct. Okay, it is 5:30. We'll start here. Okay, let us start with our first homework question. Okay, and you give me the answer here. Yes, I'm checking your answers. I'm reading your answers. You give me explanation also, not just answer. Give me the explanation also. Okay, I'm going through the explanations. Net 40 force will be normal P. I'm reading your answer. Body is cutting and observe the section. Okay. 0 because same magnitude opposite directions. 0 because summation of force is equal to 0. Okay. Unlike force is special case. Okay, so what is your answer, Alan? None of the above. As the body experienced both the piece, how you picked up, it depends upon whether the object is rigid or not. Okay. Okay. I went through all different possible explanations. Okay. Now stop answering and start listening to me. Stop answering. Start listening to me. Okay. You can see the answers of others. I have put that option on. Okay, so you can see the others answers. You also see that you people are divided into 2. That's almost 50% are saying 0 is the force. Rest of students are saying force experience is P. Okay. Let me ask you another question here, and from that question, your doubts will be more increased. Okay. Let me ask you another question here. Okay. And what is that question? For this diagram, if I ask you how much is the stress experienced by this object, then I'm sure that every one of you will say the answer is P by A. Isn't it? If I ask you how much is the stress experienced or how much is stress here, everyone will say that, sir, it is a P by A. Okay. This is the first diagram you see in any book of strength of materials or even in the machine design, right? Okay. First diagram, and this is the first formula, simple stress. Okay, sigma is equal to P by A. Okay. Again, I repeat that everyone will give me this answer only, that P by A is the stress. Okay. Now how do we define the stress? We define stress something like this. You see that we say it is something like internal resistance. It is something like internal resistance divided by the cross-sectional area. Right? Okay. So as everyone will say that the stress is P by A, so everyone should be saying that the internal resistance is equal to P, isn't it? Internal resistance is equal to P. Okay. If internal resistance is equal to P, the resistance by the body is equal to P, and you see that for resistance is like a reaction, and reaction should be equal to action. Reaction should be equal to action. Then only the things will be in equilibrium, isn't it? Right. So this statement that stress is equal to P by A by default, or in another way, in that way, it says that the internal force or the force experience is equal to P. The force experience is equal to P. Now see that everyone will say that the stress is equal to P by A. If you say that stress is equal to P by A, then obviously the force expressed should be equal to P as per your P by A definition of the stress, right? See, 50% of you saying that this is 0. This is answer is 0. Okay. If answer is 0, then there should not be any stress in this material. If the body is not experiencing any force, there is nothing to react, isn't it? So if there is nothing to react, then there won't be any internal resistance. If there's no internal resistance, then there should not be any stress. Okay, I'll give another simple example. Now suppose instead of this object, just like imagine object, let us say this is a chalk, simple white chalk. Okay. Now, if on the chalk, if we apply the tensile force, just like this force here, just the way the force is here, this tensile force here, see this force. If we apply tensile forces like this, then is it possible that the chalk will break? Obviously, right? It is very easy to break a chalk, right? So chalk will break something in vertical section. Okay. Now, see, if your answer is 0, if your answer is 0, your answer means something like this, that the chalk is not experiencing any force, and still the chalk is getting broken. It's weird, isn't it? It is very, very weird, right? So if something is getting broken, it must be experiencing some force. Okay, with 0 force something is breaking, that will change everything. Okay, and that means that won't make any sense. Okay, so 0 is out of the question. 0 is out of question. I'll give another example. Okay, just let me draw you here. Okay, is standing. Okay, and suppose if I keep a block of weight, let us say 100 Newton, that is almost 10 kg on your head. Okay, now see the free body diagram of you. From up, there is force equal to W. From ground, there has to be reaction equal to W. Now see that these two forces, this reaction and this weight, they are just like this force, these two forces, the forces on the block. Only difference is you are experiencing compressive force while the block object is experiencing the tensile force. But if your answer is 0, then in this case also you must be experiencing 0 force. If you are experiencing 0 force, then I can replace this 100 Newton by 1000 Newton 100 kg. Still you won't experience any force. Obviously you will experience force, right? So see that your answer is 0, but that is net force is equal to 0. Net force means what? Plus P minus P. Net force is equal to 0. When this is net force. When do we check this net force? We check the net force to check the equilibrium, to calculate the inertia or inertial force, mass into acceleration. Net force is equal to mass into acceleration. Okay, so there we need this net force confirm whether there is equilibrium or not. But now here we are not finding the net force, we are finding how much is the force experienced. Okay, now see how to find this. Now it is confirmed that it is not 0. So how much it is? Let us check that. Is it okay by now? Is it okay by now? Yes, cancel. Is it okay by now? Yeah, yes, right. Yes, okay. So I'll continue here. So we just confirmed that it is not 0. So how much it is? Let us see that. Okay, just because it is not 0 doesn't mean it is P, isn't it? Right. So Now see what to do, what you have to do it. What is the theory? Theory is you want to know how much is the force in this object. You simply imagine that you are cutting this object. You cut this object. Imagine that you are cutting the object. Once you cut this object, you see here, you will have two parts of this object. One is this yellow shaded part and another one is this green shaded part. We're cutting the object, right? We are cutting imaginary, we are cutting the object. Okay, so you have two parts. Now out of these two parts, you consider any one part, anyone, either left or right, whichever is convenient to you, whichever is suitable to you, whichever is easy to you. You select any part and for that part you see the force. Now see, if I select the left one, there's only this force P. Even if I select the right one, there's only this force P. Okay, and that is the internal force. That is the internal force here. Okay, so how much is the internal force here? How much is the internal force or the force experienced by the object is this one. So what is the way to get this? Cut it, see one side. You have done this. You have done this in n number of times. Where? I'll just show you. I'll just give you an example here. Okay, suppose if I take a beam like this, okay, and for this beam, if I give rollers hinge support at the left or roller support at the right, and if I apply the force P at the center, now for this example, you know that at the center, if I call this point C, the bending moment at the center point, is not zero. It's not zero. Don't say that the force is passing through point C, the bending moment is zero. No, it is not. It is maximum. And how much is that? That is PL by 4. Your strength of materials. Okay. So how this PL by 4 came? You see that this reaction of both sides will be equal reactions, half, because the load is symmetric. So now you want to calculate the bending moment at the center. You take a section here, see left hand side, and on the left hand side, you see that there is only one force which is equal to this reaction P by 2. Force is P by 2, distance is L by 2. P by 2 into L by 2 is how much? That is nothing but PL by 4. Okay. So this is how you have done it in everywhere. Everywhere I'm saying, even whenever you studied the trusses also, you did the same thing. Whenever you studied any of the chapter in your strength of materials, you did this thing only. Okay. So let me make a note here. To find internal force. To find internal force, what to do? Take a section. And refer one side only. Refer one side only. Or referring one side is sufficient. No need to refer both the sides. Which side? Whichever is convenient to, whichever will include the less number of calculations. Okay. Now internal force. What is that internal force? See that internal force means what? Whatever the object will experience. It can be axial force. Just like this example, tensile axial force came in this example, or it can be shear force, just like this SFD you studied in the center of modulus, or it can be bending moment, just like the bending moment diagram you studied in the center of modulus, or it can be twisting moment, torque, just like the torsion you studied in the strength of materials. Okay, now let me zoom out so that you can see all the things together. Yes, now see all the things together. Okay. Okay. Can you go for the next homework question? One of asking, sir, is this theory applicable for symmetric bodies only? No, no, it is applicable for anybody, everybody, anybody, everybody. It is applicable. Okay, let's go for the next one. So let us say to the left of internal section there's force P, but many forces are acting on the right hand side, the side of section 2. Okay, and you're saying that what if there are more forces acting on one side and less forces are acting on another side? See, first thing, there should be an equilibrium. First thing, there should be equilibrium. So if there are equilibrium, so don't count the number of forces. Just see how much is their magnitude, and from both sides you will get the same answer. Okay. Okay, now another student asking, sir, what if this body is a rigid body? See, even if this body is a rigid body, there will be some force experienced the body. Even if this is this body is a rigid body, because if you are applying some force, then somebody has to resist it. Somebody has to resist it. And see, okay, rigid body, you see that rigid body will not have any strain. Okay, but rigid body will have stress. No, rigid body does have stress. If you recall the stress strain diagram of the rigid body, the stress strain diagram is a vertical line passed along the y-axis. So there is a stress, there is no strain, but there is a stress. So stress is there, means something is experienced. Okay, so even if the body is a rigid body, still there will be internal force equal to P. Okay. Okay, let's go for the next homework question. This is the homework question, and homework question was like, if two forces are perpendicular to each other, we know that, like just like this. See that. See, if there are two forces, let us say this is P and this is Q. So how do we find the resultant? We find the resultant that R square is equal to P square plus Q square. This is the way we find the resultant, right? But this way of finding the resultant, is it applicable in these both cases? Okay, now post your answers. Post your answers. Okay, I'm checking your answer. Okay, whatever your doubts not answered, you note them down. Ask me the doubt clearing session. I will answer everything there. Okay. Okay, now post your answers. Case 1, case 2. Which case it is applicable? Which case it is not applicable? I'm going through your answers. Might make a sign convention required needed, but sign convention won't matter, right? We are squaring them. We are squaring them. Okay, most of you are saying that, sir, both cases it should be applicable. Both cases should be, because in both cases the forces are perpendicular to each other, right? The YZ forces and XZ force, XY forces. Okay. Now listen carefully. Listen carefully. See, we are not studying the forces from the point of view of like mathematics. We are not. We are studying them from the point of view of application, that what will be effect of the force, and the effect of the force we are interested to study is stress. Okay, now see here, listen carefully. In the first case, see the area on which these forces are acting. So this is the area. This is the area. For this area, these both forces Y and Z, Py and Pz, these both forces, they are parallel to the area. So this is shear force because it is a parallel, and this is also shear force. These both are parallel to the area. These both are tangential to the area. So these both will create the shear stresses, or these both are shear forces. Now see that if both are shear forces, then their resultant will also be shear force, because these both forces are shear forces. Okay, now come to the second case. In the second case, again you look the area. This is the area on which these forces are acting. Okay, now see that for this area, Py is tangential. So Py is shear force, but Px is not tangential. Px is perpendicular to the area. So Px is a normal force. Px is a normal force. Now see that shear force will give shear stress. Normal force will give normal stress. Now tell me that can you combine these two stresses, or can you find result of these two? If you find resultant of normal and shear, then what you will call it as? What you will call it? Combined? No, it is not. It is not useful, right? So here in the second case, you shouldn't go like this. So this is not applicable here. This is not applicable here. In the first case, it is applicable. Why it is applicable? Because in the first case, these both are shear. If both forces are shear forces, then you can find the resultant. But if one force is normal here, like the first force is a normal here, while the second force is a shear force here, we can't find, or we shouldn't find the resultant. We shouldn't find the resultant because the material, the weight behaves for the normal stress is totally different than the weight behaves for the shear stress. It is very easy to break something by the shear force. For example, piece of the paper. It is very easy to tear it than to stretch it. Right? Okay, so I repeat that you have to see the nature of the forces. You have to see the effect of the forces. If both forces are shear, you can go for the resultant. If both forces are not shear, if both forces are normal, you go for the resultant. If both forces are normal and shear, you shouldn't go for this. Okay, if you don't go for this, if you don't go for resultant in the second case, then how to solve this second case? Now see, to solve the second case, what you should do is you should calculate the norm this sigma, which will be equal to C Px by area. Then you should calculate the shear stress, which will be Py by area. I'm just considering this L very, very small so that the bending moments and all I'm neglecting. So once you calculate this, then you should go for the principal stresses, sigma 1, sigma 2. Okay. And then once you have the principal stresses, then you can go for the design of the component. Okay. Now let me zoom out so you can have a look at this discussion. Yeah. Now see it. Pune students, yesterday's lecture link is not available. You want it to be summarized. Yesterday we saw basics of the force, how to define it, moment, okay, and then parallelogram law. That's what we just saw yesterday. Nothing more. Okay. Shivam is saying where to use theories of failure to find resultant. No, theories of failure they do something else than the finding the resultant. Okay. Okay. Now let me give today's homework. Now this is today's homework. Okay. Now let me first define it. Okay. Now see that. See here. See the question here. So we have one force, 100 Newton. You can see the weight is. This is 100 Newton force, and there are two lines, OX and OY. These are two lines, and they are not axis. They are not axis, right? If they are axis, they should be perpendicular together. They are not axis. Okay. Now, if they are like this, and suppose the angles are like this. Suppose this angle. Suppose this is 30 degrees, and let us say this angle is 20 degrees. Okay, so if the things are like this, then I want you to find the components of 100 Newton along OX and OY line. Okay, now take a screenshot. Take a screenshot. This is today's homework. Okay. Okay, now some students are asking to revise what we studied yesterday. I'll just go through it. I'll just go through for every one of you. Take a screenshot. Okay, see, yesterday we saw about force. Okay, so this is like force can move the body, it can bring the body to the equilibrium. To define a force, we need three quantities. We need magnitude, we need direction, we need point of application. Okay. Then we saw theorem of transmissibility. That means we can shift the force along the line of action. Okay. Then we talked about moment. We talked about the moment. Okay, so moment is something like force into perpendicular distance. Suppose the force is along y-axis, the distance is along x-axis, then the moment is perpendicular to them. So moment is about z-axis. Okay, then we saw that equilibrium equations. So net force must be 0 in all three directions, and the net moment must also be 0. Okay, then we saw a particular case of the forces, that is couple of the forces, two equal, parallel, non-collinear opposite forces, they create a couple. Okay, then we saw that if we have two forces, and if those two forces, if they need to be in equilibrium, they should be equal in magnitude, opposite in directions, and they should be collinear. Okay, then we saw that if we have two forces, like these two forces, this one and this one, these two forces P and Q, and if they are not collinear, they cannot be canceling each other. So there will be some resultant. So this is R is the result of those two forces, and we can get it by vector method, or even we can get it from parallelogram law. So this resultant is this value R square. This expression will give you the resultant, and this tan of alpha will give angle of it. That's what we saw yesterday. Okay. Yesterday's PDF are already uploaded. Video that will be done by the management. That is beyond me. Okay. Nisarg has put the website of me. Okay, so you can simply copy it. Okay, and then everything is available on it. Okay, do it in the break, not now. Okay, so let's go about today's work. Okay, so we are going for today's work. Okay, so we'll start with this question first. Okay, this is the question from our volume 1 or classroom practice questions. Okay, so read the question. That is most important. Read the question. Read the question. Read the question. Okay. Okay, now listen to me. Now listen to me. Okay. Now see, I'm taking this line as a wing here. Now, obviously, this is which view? This is the front view, right? Not the top view. Top view will be something like this. Okay, so this is a front view, where we will see only the thickness of the wing. Okay. Now see, they are mentioning that how much is the length of the wing? 16 meters. 16 meters. So this wing is 16 meters long. Okay. Now this wing is subjected to lift force. Lift force. Okay. So lift force means in which direction it should be. It should be upward. Right. And that lift force is not a constant value. It is changing from 0 at the tip to some value 360 Newton at this fuselage. Okay. So what is the fuselage here? You see that if you see the aeroplane, see here, this fuselage means it's the main body of the aeroplane. Okay, so this is the tip of the wing. Tip of wing. Okay, so where the force is said to be 0, and at the main body, the force is 360 Newton meter. Okay, so in this one, I will take this as a tip. So at tip, how much is the force? 0. At the main body, that means this body, how much is the force? 360 Newton per meter. And you see that how I'm showing it. I'm showing it upward. How I'm showing it? I'm showing it as upward. And why I'm showing it upward? Because it is a lift force. So lift force should be lifting anything or something. Okay, so it should be acting upward. Okay, so force is 0 at the tip. force is 360 Newton per meter. That is the load intensity at the main body of the aeroplane. And how the force is varying? The force is varying according to this formula. And that formula is this formula. See, 90 into root x. 90 into root x. That is the equation. So root x means the relation will be parabolic. So see, this force will vary like this, parabolically. Okay, and what is this equation here? See, this equation is 90 into root x. In this equation, what is x? X is also mentioned in the equation. You see that x is measured from the tip. So if I show that in the diagram, see, from the tip x is measured. So at the tip, how much is x? 0. If I put that x is equal to 0 in this formula, then this will be simply 0. So that will be simply this 0 as it is shown or it is mentioned in the question. If I go to the main body at this point, let us say this point is point B. So at this point B, how much is x? X will be equal to 16 meters. And if I keep x is equal to 16 into this 90 into root x formula, root 16 is 4, 90 into 4 is 360. That is same as this value. Okay. Now, what is asked to us? We are asked to calculate the resultant load, resultant lift, and its location. Now understand that resultant load means whatever is the area of this diagram. I'll make note that first. A resultant load means total load. Okay, total load means area of the loading diagram. Area of loading diagram. Now you might be confused here. So how it is? Okay, I'll give you an example. So let me take an example here. Okay, I'll take an example here. Okay, so I will take a cantilever beam. One end is fixed, one other end is free, and see, we are applying load like this. What do we call this load as? We call this as uniformly varying load. Okay, let us say this is omega. Now can it, and let us say the length is L. Can you tell me how much is total load here? I'm waiting for your replies. How much is total load here? I'm waiting for your replies. Yes, very good. Question, it's not omega into L. Omega into L will be there if it is a UDL, uniformly distributed, right? This is UVL. So how much this will be? This will be 1/2 omega into L. Okay, now see here. This triangle has how much height? Omega. This triangle has how much base? L. So how much is the area of the triangle? Area of the triangle is same as this total load. Okay, actually it is vice versa. The area of the loading diagram is equal to total load. So if I apply that definition here, I just have to find how much is the area of this diagram, and that gives me the first answer. So I'll just write it like this. Therefore, the resultant load R is equal to area. Now see, this is a parabolic curve, and for the parabolic curve, to find its area, what we will do, we will take a small strip here. This small strip will take this small strip of width dx and height y. Now listen carefully. Now see, for this small width, for this small strip, see, vertical height is y, and that vertical height means nothing but 90 into root x, right? It is 90 to root x, and this x, now it's this x, It should be up to this one, right? Okay. Now, if I write this for the resultant load, now see, for this small strip, the area is, height is y, width is dx. So y dx is a small area, but we want the total area. So total area means we have to integrate this. We have to integrate this. Okay, let's do that. So I'll write it here. Now see, this resultant load R is equal to integration y into dx. We'll go like this. Integration y is how much? Y is 90 root x into dx. The variable here is x. X is changing from tip to the main body. At tip x is 0. At main body x is 16 meters. Keep listening. I'm going to solve this without calculator. Okay, 90 comes out. Then x root x is nothing but x to the power 1 by 2. So if you take integration, this is going to be 1 by 2 plus 1, that is 3 by 2, divided by 3 by 2 will come here, and we will have limits which are 0 to 16. Again, we are going without calculator. Okay, now see, 90 by 3 is 30. 30 into 2 is 60. So first term is 60. In bracket, if you put the limits, this is 16. 3 by 2 minus 0 is equal to 16 into. Okay, now see, 16 60 into, now see, this we can write as 16 to the power 1 by 2, and this entire cube, right? Okay, so 60 into 16 to the power 1 by 2. See, this is nothing but root over. Okay, so 16 root over of 16 is how much? That is 4. 4 to the power 3. That is nothing but 64. Do this manually. So last digit will be 0. 6 into 4 is 24. 6 into 6 is 36. 36 plus 2 is 38. This is force, so this should be Newton. And like I told you that as soon as you get one of the answer, check the options. Like I told every time. Okay, so check the options. So if you check the options, see that in options at one location only you have that value, that is option A. So now you have the answer. You don't have to calculate the other value. So you have the answer here. Only thing you have to do is you have to do it again. Okay, just to confirm the calculations. Okay, now see all the steps again. I will explain how to locate it. Okay, how to locate the resultant. Okay, but first you understand this value. Okay. Okay, what is the lift force? See, when a body is moving through and a fluid, there will be drag and lift forces, right? So this is the lift force. This is the lift force. Okay. Okay. Now this is for the resultant. Okay. Now let us go for the location of it. The location of it. Okay. Now come back to this example again. Come back to this example. Okay. Now see here, how much is the total load? See, this much is total load. Now, can you tell me this will be acting at what location? I'm waiting for your reply. This total load, where should I put it? Where should it be put? Yes, tell me. I'm waiting for your reply. Yes, very good. See, it is not at L by 2. It is not symmetrical loading, right? It should be at the centroid. It should be at the centroid. Okay, now whose centroid? Centroid of loading diagram, not of the beam. We are not showing the weight of the beam. No, we are showing the load. It should be put at the center of the loading diagram. See, you might be confused about loading diagram. See, this is the loading diagram. Loading diagram means what? The diagram which represents the variation of the load. right? So this is the loading diagram. This is the loading diagram. Okay, so this load, which is half omega L, it should be put at the center of it. It should be put here to calculate the moment. So this will be omega L by 2. And how much is distance from this side? For triangle, this distance is 12 by 3. And from this side, it is L by 3. So the next point is the resultant will act at the center of the loading diagram. I'll first make that note. Okay, so a resultant will act at centroid of loading diagram. Okay, now we should know how to locate the centroid. Okay, so how do we locate centroid? You see that we need x distance here, right? So I'll call it as xg. This will be integration for this total force. Okay, that will, okay, total force divided by the area. Total force divided by area. Now this will be, you see that this total force is how much? Total force is y into dx is integration is total force. Or if you go for this small one, the force is y into dx. Okay, area, and into x, the moment. Now that should be same as this y into dx. Now don't cancel this y dx because they are inside the integration. Okay, so next, if you write it here, it will be like this. Okay, so in the numerator, y means what? 90 root x into dx into x. In the denominator, again 90 root x into dx. Okay, we can even solve this with our calculator. Now see how 90 will get cancelled. In the numerator, we will have, see, x to the power 3 by 2 into dx divided by x to the power 1 by 2 into dx with same limits again. Okay, now the numerator integration will be x to the power 5 by 2 divided by 5 by 2 divided by x to the power 3 by 2 divided by 3 by 2. Now both the numerator denominator 1 by 2 will get cancelled, and we will have this 3 by 5 here. Okay, and this both limits are 0 to 16, right? So x to the power 5 by 2 divided by x to the power 3 by 2 is nothing but x with the limit 0 to 16. Okay, so this is nothing but 3 by 5 of 16. Okay, so this is 0.6 of 16, that is 16 into 16 into 3 is 48. 48 by 5 is going to be 9.6 meters. And see, that is same as the option A's answer. Option A's answer. Okay. Here I think I wrote L by 2, but it's L by 3. Okay, the proper saying I wrote it L by 2, but it's L by 3. Okay, now is it okay? Okay, I repeat xg again. Okay, I'll just redraw this. Okay, now see, we have this loading like this. Okay, and we want to replace this load by one resultant load. Okay, now you see that this resultant load we will take at a distance xg from this point. Okay, so resultant means what? Resultant is going to replace all these by this only one value, right? So whatever is the moment, of all this parabolic force, if this moment is m, moment here also should be m. So this moment is going to be equal to, you see that in the first case, moment is force into distance. Force is nothing but a load here. So load is how much? Load is y into dx is load into x is the moment. In the second case, the moment is simply r into xg. Okay, so if I rewrite this again, this xg will be equal to integration y dx into x divided by r. R is nothing but y dx only. No? So that is how the result is calculated. Is that okay? Okay. Okay. Now again, if some small doubts are not clear, you just write them down and ask me in the doubt clearing session. Okay, I'll go for the next numerical. I'll go for this numerical. Okay, now read the question. Read the question. Read the question. Okay. Okay. Now see what we are asked here. We are asked to find the result of these forces. Right. Okay. Now see that how many forces are here? 4 forces are here. See these 4 forces. Okay. Now see what is the standard way of finding the resultant, or any case. See, resultant is R is equal to summation fx square plus fy square, summation fy square plus summation fz square root over this. Okay. Now this R will be simply equal to sigma fy if we don't have force in a direction, if summation fx is 0 and summation fz is 0. So see, in this case, all the forces are in vertical direction only. Forces are in vertical direction, so sigma fx is 0, sigma fz is 0. So R simply will be equal to sigma fy. Okay. Now let's put these values here. Now see, therefore the resultant R is equal to, now see 100 is upward, so plus 100. 150 is upward, so again plus 150. 25 is downward, so minus 25 plus 200. Now 100 plus 150 is 250 plus 200 is 450 minus 25 is 425. Now this is plus value, so it must be upward. Okay, and like I told you that as soon as you get any one value, check the options. Check options. And as you check the options, you will come to know that there is only one option with this value, that is option A. Okay, so you have the answer. You have the answer. You don't have to check the second value. This is how the most of the exams will conduct it, or most of the exams will put questions like this. Okay, so you have to look for the smart way of answering, not just keep on solving. No, you have to do these things. Okay, so instead of calculating here the result, location of the resultant or the distance of it, you calculate resultant 2 times just to ensure the calculations. Okay, now see the next point. So if you want to locate the centroid, okay, if you want to know how to do that, then you choose any point. For example, if I choose point A, so from point A we will locate it because it is asked to do it from that point only, point A. So let us say the resultant is somewhere here. Let us say we're assuming it at this. Okay, so let us say this distance is distance x. So resultant means resultant is capable of replacing all these 4 forces. Okay, so effects must be same. One of the effect is a moment. So let us take the moment. Let us take the moment about point A. So moment also must be same. Moment about point A. See, I am not writing it 0 because this is not equilibrium case. This is a resultant case. Resultant means there is something non-zero value. Okay, so moment must be same of individual forces together and the resultant. So if I take the individual forces here, this 100 will give me no moment, so 100 into 0. This 150 will give me anti-clockwise moment, which is a plus. So 150 into distance is how much? Distance is 0.9. Now next force is 25, which is downward, which will give me clockwise moment. So minus 25 into distance is 0.9 plus 1.2, which is 2.1. Then this 200 will give moment in this direction. So again positive. 200 into the total distance, which will be 0.9 plus 1.2 plus 0.75. Now this value should be equal to moment of the resultant, which is r into x. Now again, if you solve this, I'm sure you will get that same as option A, which will be 1.53 meters. Okay. Now again, you read the question and see the approach. Okay, now one of the students saying this, what if the options are not given? Yes, in that case, no one can do anything, right? If options are given, then we can be smart. If options are not given, like if it is an NTQ question, numerical type question, then we can't do anything. We can't do anything. And in numerical type questions, you won't be asked two values. You will be always asked only one value. Okay. So can we go for next numerical? Okay, we'll go for the next one. Okay, we'll go for this numerical. This numerical was asked last year. Okay. Now read the question. Read the question. You first read the question. Read the question. This was asked last year. Read the question. Okay, now in the diagram, you see that three forces are given. So this force P, this force P at C, and this force P. Okay. And what is asked to us is what will be equivalent system, that is force and moment, at which point? At point A. At this point. Okay. Now the easiest way to calculate this is shift all forces, shift loads, loads means force and moment, shift all loads at A. That will be simplest way. Okay. So let us start doing it. Okay. Now we'll start with this force P here, this force. Okay. Now see, if we shift it from point D to point A, no moment will come, right? Because the force is passing through point A also. It is in the same line. So this force will come, only force, no moment will come. That is from point D. This has come from point D. Okay. Now let us shift this force. At point B, there is a force, no? This force. Okay. Now see, if we shift it here, if we shift that force here, force will come and a moment will come. Force will come and moment will come. This moment will be how much? This moment will be clockwise, because see, it will be like this, clockwise. And how much the magnitude? Force into perpendicular distance is A. Okay. Now that is due to this point, this load at point B. Okay. Now if we go for this point C, this point, I'm using C color combination, this C. If we shift it here, the force will be like this first, and moment will come, Now this moment will be equal to, again, force into perpendicular distance is A. Okay. And now this all is happening at this point, which is point A. Okay. Now see, out of these things, some things can get cancelled. Equal opposite things will get cancelled. For example, see, this P and this P, they will get cancelled. So for point A, as those P's are getting cancelled, now what will remain there? Force remain is vertical force P. Okay. Now there are moments also, and you see that those moments are both clockwise. Those both moments are clockwise, so they will be added together. They will be added together. So those moments will be added. So we will have m plus m moment because they both are clockwise. So that will be simply 2pa. Okay. Now see options. See are the options. Which option is correct here? Option B is correct here. So system 2 is the answer here. Okay. Now I'll just zoom out. Yes. Okay. 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 See, one of students asking, sir, how to ship this load. Okay, this load. Okay. Now see, the force is here. If you shift it to point A, force will come and a moment will come. Force will come and moment will come. If you change the line of action, if you shift the force from its line of action, the moment will come. Moment will come. Okay. So that's what simple thing is here. Is it okay? Okay. Can I go for next one? Okay, you see that we are shifting the force, so directions will be same. If P is downward, the shifted force will be also downward. Okay, as we are shifting it, the same direction should be continued. We are not finding the force to bring the system in equilibrium, nothing like that. If you have to bring the system in equilibrium, then opposite forces should be brought. So we don't have to bring the system in equilibrium. We are not finding the reaction. We are not finding the reaction. We are not interested to do the equilibrium here. We are just shifting the things. Okay. Okay. Now there is a similar question like this in this year's GATE exam. Okay, I'll just take it there. Yes, it is. Yes, this question. Similar question. Okay. Now read the question and post your answer. This year in XE paper, engineering sciences paper. Okay, read the question and post your answer. I'm waiting for your replies. If any small doubts are not answered, just note them down. Ask me in the doubt clearing session. It's almost impossible to answer everybody's individual doubt. Small individual doubts, please ask me in the doubt clearing session. Okay, now see, we are again asked to find the equivalent force system, right? At point B. So we have to shift the forces at point B. So if we shift the force at point B, this 40 kilonewton, it will come. This 40 kilonewton as it is, it will come. And as we are changing the line, the moment will come. And you see, at point B, the moment will be in this direction. Moment will be in this clockwise direction. Okay. And how much is this moment? See, the moment is force into perpendicular distance. Force is how much? Force is 40,000 Newton. 40,000 Newton. And how much is the distance? Distance is 100 millimeters. 100 millimeters is nothing but 100 by 1,000 meters. So this will be in Newton meter now. Okay. Now this 1,000 will get cancelled. 40 into 100 is 4,000 Newton meter. Okay. And again, what is the direction here? Direction is clockwise. Okay. Now see the options. How to look at the options? See, m is equal to 0 is not possible because we are changing line of action. So this is wrong. This is wrong atom. This is wrong. Okay. Now moment. in last two options we have moment, but this moment is clockwise, so counterclockwise is not possible. So this should be only answer. Okay, even if you match this moment alone, you can get the answer. And the second part is obviously also correct, that 40 kilonewton, and be specific that it is about minus y-axis. Axes are mentioned in the question, so this is obviously plus, and the downward will be minus. Okay, similar questions you must have come across in machine design, okay, where you will be asked to calculate the stress on this hook. Okay, so you know the things like 40 Newton will bring the tensile stress, and then M will be bending stress. Okay, things like that. Okay. Okay, now see again the direction. See, this 40 is downward, so this will be also downward. You are just shift it. I'll just make a note here. Shift loads, whatever loads are there, at B. Shift loads at B. Okay, so or you see this way also. See, this 40 is pulling this point A downward, so it is pulling this point B also downward now. So that's why the force should be in the same direction. And the second direction is a moment. See, this is the direction of the moment. It will rotate it clockwise. Okay. Okay. Okay, individual doubts I will answer in the doubt clearing session, because it's almost impossible to answer everybody's individual doubt. How to decide this? It is clockwise. See, it is like this. See, this is the rod. You are applying force P here, and suppose this is hinge point. So this rod will rotate in which direction? This rod will rotate in this direction, right? That is clockwise. So similar thing is here. Okay. Okay, I'll go for the next one. Okay. Okay, now I'll go for equilibrium of three forces. Equilibrium of three forces, and those three forces, I will take them as, let us say, P1, P2, and P3. These three forces. Okay, what do we know up to now is, we have seen this, that if we have two forces, then if they have to be in equilibrium, then they should be equal in magnitude, they should be opposite in direction, and they should be in one line. Collinear they must be. That's what we have seen, but that is for two forces. If we extend our discussion for the three forces, now let us see what should be the conditions here. Okay, now let me take a random object. So on this object, I'm going to apply three forces, and those three forces are P1, P2, and P3. Listen, don't do anything, don't post anything. Okay, just listen. This is concept. Okay, so let me pick P1 first. So let me apply P1 like this. So this is P1. Okay, now let me apply P2 here. Now suppose I apply P2 like this. I will just make it like this. P2, this is P2, which is passing to this point. Okay, now see that these two forces, P1 is passing through A, P2 is passing through B. Now, are they concurrent? Concurrent means what? Are they passing through one point? Now it seems they are not. But if we extend their line of actions, like this P2 will go like this, this P1 will come like this. Now see that if I show them at this point by the theorem of transmissibility, they are passing to that point. So I will say that this P1 and P2 are passing through one point. Okay, because I can shift the force along the line of action. Okay, so let me name this point as point C. Okay, now keep listening. Now again, the same body, the point C now I'm taking, I am showing two forces up to now. Third force will come. So now I will shift these two forces to point C. Can we do that? Yes, we can do that. Which theorem? Law of transmissibility. P1, P2. And understand that these both the diagrams, they are same. They are same, right? We can transmit the force along its line of action without changing the effect. So these both the diagrams are same. Okay, next point. Okay, now focus on the second diagram. This diagram, second diagram. In this diagram, we have two forces. Third is coming. Third is coming. Okay, we have two forces, and these two forces, they are not collinear. So let us say the angle between these two forces is theta. So I can find result of these two forces. Okay, so I'll make a note here that I'll say R is a resultant of P1 and P2. Now, how do we calculate the resultant? We calculate the resultant by the help of the parallelogram law. And how is that law? That law is like this: R square is equal to P1 square plus P2 square plus 2 times P1 into P2 into cos of angle between them. The angle between them is theta. Angle between them is theta, right? Okay. So R is a resultant of these two. R is a result of these two. So now what it means? It means that if I take this object, this body again, if I take that object again, then the resultant will also pass through point C, and that resultant I will show, I will assume it is like this. It is horizontal. Okay. Now again you see that these both diagrams are same, or these all three diagrams are same. See properly. Here, two forces are there, P1 and P2. Third is coming. Two forces P1 and P2 are there. In the first diagram. Second diagram, I just use the theorem of transmissibility. And in the third diagram, I replace this P1 and P2 by its resultant. So all these are technically same. All will have same effect. Okay. Now come back to the statement. The initial statement is that how many forces we want to apply? We want to apply three forces. We want to apply three forces. As we want to apply three forces, and you see that out of those three forces, I am done with the applying two forces. Now I have to go for the third force. Now see the third diagram and tell me how should be P3 so that the third diagram will be brought into equilibrium. I'm waiting for your replies. I'm waiting for your replies. I am waiting for your replies. How the force should be P3. How the third force P3 should be. Yes, very good. Now see, if I'm talking about P3, now I'm left with only two forces, P3 and resultant. P3 and resultant. So if there are only two forces, how two forces are in equilibrium? Equal, opposite, collinear. So this P3, the force P3 must be like this. This force P3 must be like this. And how much it must be? It must be equal to R. Then and then only these things will be in equilibrium. If I show this force P3 in the previous diagram, you see that the force P has to pass through point C. So it will be like this. It will be like this in the first diagram. Now, what is the important point here? You see that these three forces, they must pass through one point to be in equilibrium. Three forces must pass through one point for equilibrium. I'll just make a note here. Okay, now see. Three forces must pass through one point. Must pass to one point. And what this condition is called as, forces passing through one point, it is called as concurrent. Okay, for equilibrium. for equilibrium. Okay, now they must pass through one point. Okay, and they should satisfy equilibrium equations also, and they should satisfy equilibrium equations. Obviously, they should satisfy equilibrium equations, which means that their triangle should be a closed triangle. They should satisfy the equilibrium equations. Okay, one more point, very important point. Now listen this carefully. Now see, in this step, the force P3 is equal to R, value I'm just writing, equal to R. And what is R? R is resultant of P1 and P2. Resultant of P1 and P2. Isn't it? We discussed that. Now, any one force must be resultant of any other two forces. For example, this P1 should also be equal to resultant. P1 should also be equal to resultant of P2 and P3. Similarly, this P2 should also be equal to resultant of P1 and P3. Take time to understand this. Take time to understand this. Okay, let me zoom out. Yes, now you can see the things together. Okay. Now these forces are concurrent, and wherever that point, concurrency point is there, that can be inside the body, that can be outside the body. It can be anywhere. It doesn't have to be inside. It can be outside also. It can be outside also. Okay. Now let's go for the next point. Okay. Now the next point is a Lami's theorem. Next point is a Lami's theorem. Okay. Now listen carefully. I will draw it in front of you. Now see, I'll take the forces. Okay, so this is one force. Then the next is force like this, and another force is like this. Okay, let us say these forces are P, Q, R. Okay, let us take these angles. Okay, let us say these angles are, let us say this is θ1, θ2, and θ3. Okay, now listen carefully, listen carefully. See, these 3 points, they are passing through this point O. Okay, and that was one of the conditions that the forces must be in equilibrium. Forces must be in equilibrium. So Lami's theorem is applicable for 3 forces in equilibrium. 3 forces in equilibrium. Don't apply Lami's theorem for 4 forces. It is not applicable. Why it is not applicable? Because it is based upon sine rule. It is based upon sine rule, and sine rule is applicable for triangle. Triangle has 3 sides. 3 sides means 3 forces. Okay, we saw that parallelogram law was based upon cosine rule. Parallelogram law is based upon cosine rule, and Lami's theorem is based upon the sine rule. So it is applicable for 3 forces only. Another important thing, don't miss this. The next important thing is all 3 forces should be acting. All 3 forces should be acting either away or towards the concurrency point. The concurrency point, the point of intersection through which the forces are passing. So all 3 forces either should be towards that point or away from this point. So if I see this example, in this example, all 3 forces are taken outside. Don't play with the combination. Don't play with combination, because if you play with the combination like one is away and two are towards the point, then the answer will be wrong. Then the answer will be wrong. Okay, keep listening, keep listening. Okay, next point. Then what is this? What is this theorem? This theorem says that the ratio force P divided by, now see that apart from force P, other two forces are force Q and force R. What is the angle between these two? Angle between these two is θ3. So you should take sine of that, and P divided by that sine θ3. Now this is equal to, take the second force, force Q. Apart from force Q, what other forces are there? Apart from force Q, what other forces are there? There is P and R. What is the angle between them? θ1. So you write sine of θ1 here. Now this is equal to, what will be last stage? Last will be R divided by angle between P and Q is going to be sine of θ2. This is the Lami's theorem. This is the Lami's theorem. Don't write, just don't write anything anywhere, or don't comment also. Keep listening. Okay. Now we know that these three forces must be in equilibrium, so we can use the equilibrium equations here. Now see that either we can use the Lami's theorem or we can write the equilibrium equations. Now tell me what equilibrium equations we can use here. I'm waiting for your reply. You give me those equations. Don't just give me number 1, 2, 3. Give me those equations. Tell me which equations we can use here. I'm waiting for your reply. Okay, I see your answers. Okay, keep answering, keep answering. Okay, one of the students saying, sir, all 6 equations we can go for. Okay. Okay, okay, keep going, keep going. Keep answering, keep answering. Shastri, you are saying only 3. Which 3 I want to know? So Saitesh, I want to know which 3. Just don't give me the number. Tell me which equations. Okay. Okay, now stop answering. Stop answering. Listen carefully. Listen carefully. See, these forces are in XY plane. These forces are in XY plane, right? So if forces are in XY plane, then obviously we can use sigma fx0. We can use sigma fy0. Now see that as forces are in XY plane, we think that moment about z-axis 0 can be used. We think that. That's what we saw when we saw the forces in XY plane. But you see that these forces are passing through this point O. So if you take moment about point O, how much will be moment of all forces? 0. So is this equation helpful? This is not useful, or this is not helpful. So only 2 equations which will help you are these 2 equations. Okay. Now some students were saying that, so you can go for sigma fz0 also. But you see that in this case, do we have any force in z direction? These all 3 forces are in XY plane. So no component of these 3 forces will be in the z direction. That is why we can't use sigma fz0. Okay, so this is not useful. Not useful. Even if you try to apply it, you will get left hand side 0. So 0 is equal to 0 is of no use. Okay. Now listen carefully. This is a question here. This is a question. Okay. Now, if you see the arrangement here, either you can use the Lami's theorem or you can use the equilibrium equations. How many equilibrium equations are here? Sigma fx0 and sigma fy0. Okay. Now, if I look at the equilibrium equations, how many equations are these? These are 2 equations only. Moment is 0. Okay, but if I look at the Lami's theorem, which is alternative to the equilibrium equations, Lami's theorem will give how many equations? Can you tell me this? Tell me this. This Lami's theorem will give me how many equations? Let me see. Can you answer that? Lami's theorem will give how many equations? Yes, very good. It will give three equations, right? You compare P and Q, first two ratios, one equation. First and third ratio, another equation. Second and third ratio, another equation. So this Lami's theorem will give us how many equations? Three equations. Okay, now see there is a like there is mismatch. There is inconsistency. What is inconsistency here? That if you use equilibrium equations, you can have only two equations. But if you use Lami's theorem, you will have three equations. Okay, now listen carefully. If you use the Lami's theorem, you think that you will get three equations, but those sorry. Come back to this. Okay, so if we use Lami's theorem, we think that we get three equations, but out of these three equations, only two equations are independent. Only two equations are independent. Now, why it's so? Because you understand that this force R is a resultant of, it is resultant of P and Q. It is resultant of P and Q. So if you know P and Q, you know resultant, you know R. So you don't have to have equation to find it. You don't have to have another equation to find it because it is already resultant. And at the same time, you see that these all three angles together should be 360 degrees. So this angle theta 2 must be equal to 360 minus theta 1 minus theta 3. So these are dependent things. They are not independent things. Now, how many independent equations you have here? Two. How many equations you have in the equilibrium equations? Two. Now the data is consistent. In the simplest meaning, you can find only two unknowns here. That is what the basic meaning here is. Okay. Now see all the things here. See the things together. Okay. See all the things. Go through all the things. Okay, one of the students asking this, sir, why moment equation is not useful here? Okay, you see that all three forces, P, Q, and R, these all three forces, they are passing through point O. No? They are passing through one point. As these forces are passing through one point, if you take moment about that point, can you get any moment? No moment, right? Moment will be zero. So as the moment is zero, that equation is not useful. No? That equation is not giving you anything. Okay, that is why that equation is not useful here at all. Okay. Okay, next point. You see here, either we can go for the Lami's theorem or we can go for the equilibrium equations. So in the example, whichever is convenient, whichever is easy to go for, that way we'll go. So how to decide that? That we will practice. Okay. Now let's go for a numerical. Let's go for a numerical. This numerical is from the GATE exam. This is from the GATE exam. You see the arrangement here, and the question statement is. On question statement, you can guess from the options that we are asked to calculate this TAB, tension in AB, and tension in AC. So these things are asked. Okay. Now read the question or see the diagram. See the diagram. See the diagram. Okay. Okay. This is from the GATE exam, so calculator is available. Calculator is available. Okay. Notice one thing, that suppose if we calculate TAB or TAC, see the options, all options are different. So if you calculate one of these, that is sufficient. If you calculate one of this, that is sufficient. So you go only for one value. Instead of calculating both values and comparing with all the options, you calculate one value two times, right? So I'll go for TAC. Any one of these calculators are available. So see, the formula will become TAC divided by, now for TAC, what angle should be taken? You see that this angle should be taken. Angle between other two forces. Other two forces are this 600 and TAB. So this angle is nothing but 90 plus 60, which is 150. So this will be sine 150. Now this is equal to 600 divided by, okay, now which angle we should take? We should take angle between these both tensions. Okay, now see, this angle will be 90 degree, right? Because this is 180 minus 60 minus 30. So this formula will become sine 90. Okay, now we know that sine 90 is 1. So this TAC will be equal to 600 into sine 150. Now sine 150, now you have the calculator, you can use it. Otherwise, you can see like this. Sine 150 is nothing but sine 90 plus 60. Sine 90 plus theta is cos theta. So that will be cos 60. Cos 60 is 1 by 2. 600 by 2 is 300. Okay, so 300 TS is the second value. So this is 300 here, only 300 here, only 300 available in option A. So that is the answer. Okay. Now, again, I'm saying you that you go for only one value. One value calculating is sufficient. You calculate this one value two times. Understand this smart. Okay, instead of calculating two values, you just calculate one value two times. So your calculations will be confirmed. Okay. Okay. Now let us check one value here. Let us check one value. This is for just some extra discussion. Now, can you calculate the resultant of TAB and TAC? Okay. Now see, what are the values of these? See, from the option A, this is 520 Newton, and this is 300 Newton. Isn't it? Okay. Now, can you calculate? Let me see what you can do here. You have calculator. Use the calculator and calculate this. Use the calculator and calculate this. Calculate the result of these two tensions. Okay, you are giving me answer approximately equal to 600. Now see how I will calculate. Now it will be like this. See, this will be cosine rule, right? This is TAB square plus TAC square plus 2 times tension in AB into tension in AC into cos of angle between them. Angle between them is 90 degrees. So this is cos 90. This entire bracket to the power 1 by 2 or square root, right? Because left hand side is just resultant. Okay. Now, if you put values here, this cos 90 is 0. So this will be simply, first one is 520 square plus 300 square and root over that. This value will be approximately equal to 600 Newton. And see, that 600 Newton is equal to this value, or this is 600 Newton. That is what I said, that if the system is in equilibrium and if you have three forces, then any one force should be equal to the resultant of other two forces. That we just mathematically also confirm here. Technically, we have discussed it. Now, mathematically, we just confirm it here. Okay. Okay, let's go for the next point. Okay. Okay, so next point. Yes. Okay. Okay, listen carefully. Okay. Now, whenever there is a contact or support, for example, if I take a block like this, okay, and if I keep this block over a ground surface, so this is a ground surface here. I can keep it over other block also, okay. For reference, I have just kept on the ground surface. Okay, so here, this is the contact surface. This is the contact surface. This is the contact here. Okay. Now question is, if there is a contact, what kind of reactions it can give? What kind of reactions? So it is very easy to identify. For example, if you apply force like this, let us say this force is force P. Now this force will be resisted by a reaction here. So let us say this is the reaction R here, and that R must be equal to how much? R is equal to P. Okay, one more. Suppose we apply force like this. Let us say this is force P2. Let us say this is P1. Now this force will try to move this block. And let us say that this block is a rough block. So there will be friction force. And suppose the friction is more than the P2. So the friction force, how it will act? See, the friction force will act like this. This will be friction force. Okay. Now listen carefully. See that this contact surface is giving two reactions. One is this R and another is this F. Okay, now see that this reaction R is perpendicular to the contact surface, while this frictional force is parallel to the contact surface. R is perpendicular, frictional force is parallel. So we can say that the contact surface can give two reactions. Contact surface can give two reactions. One is perpendicular to the surface, which we will call as a normal reaction. Why normal? Because it is perpendicular to the surface. Another is a parallel or tangential to the surface, which we call as a friction. Now that point is summarized here. Okay, now see this. Normal reaction, which will be perpendicular to the contact surface, and there will be friction force, which will be parallel or tangential to the contact surface. Okay, suppose somewhere it is mentioned that the contact surface is smooth. Okay, if it is smooth, the friction force will become 0 because smoothness can't give any friction. Okay, now now see these things together. Okay. Okay, can I go for the next one? This was a simple one. Can I go for next? Yes. Okay, now this one is a conceptual, very interesting also. Okay, very interesting, very useful also. Okay, this will clear a lot of doubts, but actually the doubts it clears, those doubts don't come to students mind. That is a problem. Students think that okay, it is not a big point, it is not a big deal, but it is a big deal. If you really want to understand the technical things. Okay, if you really want to make sense, these are very important things. Okay, so I'll I will explain what I'm saying now through the examples, because whatever I'm saying needs some reference. Okay, so let me first discuss the concept here. Listen carefully, it's very interesting. You won't find it anywhere, believe me that. Okay, So I'm being specific here. I want to be very specific with the things I'm going to select. And I am taking a rod here. Okay. So see, the first point I'm specific about is I am taking a rod. Okay. This is a straight rod, isn't it? This is not a inclined rod, or this is not a like L-shaped rod or curved rod. It is not. It is a straight rod. So whatever theory I'm going to discuss here, or whatever conclusion I'm going to make, that is applicable only for these things. Okay. Then now I want to apply the forces here. Okay. Now see the forces I'm applying. See, one force like this, another force like this, another force like this. I will apply forces here also. Okay. Now that's it. That's it. I don't want to apply any more forces. That's it. I'm done with the forces. Okay. Let us say this is P1. Let us say this is P2. Let us say this is P3. Let us say this is P4. This is P5. And this is P6. Okay. Now notice that what I'm being specific about something, that whatever forces we are applying, those forces are limited to the ends of the rod. So the second condition I am being specific about is loads, whatever loads are there, 1 to 100 loads. Okay, those loads are at ends only. No load is at the center. No load is at any location other than the end. No load. No load. Okay. It also means that I have to neglect the weight also. I have to neglect the weight also here. Okay. Because if I show the weight will act at the center, right? So I shouldn't take it also. Okay. So whatever result I'm going to say, that result is exclusively applicable for these two cases. What these cases are: straight rod loads are at the ends only. Okay. Now see the next point. Okay. Now look at joint B. Let us say this force P1 is making angle theta here. Okay. Now if I see joint B, if I see the joint B, at joint B, I'm talking about at joint B. Okay. So if I see these forces, I can find the net force in X direction at point B. See how much that will be. That will be simply P2 plus P1 cos of theta. I'm sure you are with me here, right? Okay. Similarly, I can find net force in Y direction at point B, which will be P1 into sine theta minus P3. Right? Okay. Now I can do the same thing at joint A also. I can find the net force in X direction, net force in Y direction at joint A also. And then you see that. I'll take this rod again. The same rod, okay, with same ends. Now I will replace this P1, P2, P3 by their resultants like this. Okay, so this is sigma fx at B. This is sigma fy at B. Similarly, I will do the same thing at A also, which will give me something like this. One is like this. And they'll be vertical also. Let us say it is downward. Okay. So this will be net force in X direction at point A. This is net force in Y direction at point A. Now, what is the interesting thing here? Interesting thing is these two are the same diagrams. These two are the same diagrams. We just took their components, right? These two are the same diagrams here. Okay. Now let's continue here. Now see that we are talking about equilibrium by default. Or I'll just make a note here. Okay. So here equilibrium is available. The rod is in equilibrium. Rod is in equilibrium. Okay. So if equilibrium is available, I can use the equilibrium equations. So if I start using equilibrium equations, suppose I start with the moment equation. Moment equal to 0. Tell me, I'm waiting for you to replace. Tell me this moment equation I should apply at which point? Moment equal to 0 is applicable at which points or which point I am waiting for your reply. Is it applicable at A or B or at center or at some other point? I'm waiting for your replies. Where it is applicable? I'm seeing your answers. Why I'm asking? Because this is an interview question, because it is confusing point for everyone. And if you see the others answers, then you will see that different peoples are giving different answers. So it should be addressed properly. Some are very pure correct, very pure correct. Now listen carefully, see the answer. Now stop writing. See the answer. Moment, net moment is equal to 0 is applicable at each point. Is applicable at each point. At each point, this net moment should be 0. If net moment is not 0 at some point, then the body will rotate about that point. Body will rotate about that point. Okay, understand this. Understand this. Okay, so the moment you can take anywhere, inside the body, outside the body, inside body, at any point. That is why you must have seen that at different examples. Sometimes it is taken at the left end, sometimes at the right end, sometimes at the center also. Okay, so at any point, let me pick any one of these points. So let me say point A. So if I write the equation for the point A's moment, understand that at A, only this force will give moment. Every other force component is passing through point A. So the equation will go like this. See, this is counterclockwise. So plus net force in Y direction at point B into the distance, perpendicular distance is L. This should be 0 for the equilibrium. The length is not equal to 0. So this net force in Y direction at point B should be equal to 0. This must be equal to 0. This must be equal to 0. Okay. So this has to be condition for equilibrium. We are talking about equilibrium things. Okay. Now next. Okay, see, if I use sigma Fy0, sigma Fy0. Now listen carefully, sigma Fy0 should be written for all the points, not for one particular point. Net forces on entire structure or entire rod. So if you see the forces in Y direction, if you see the forces in Y direction, now see that this force is already become 0. So the next vertical force, there's no one to balance this force. So that force must also be 0. So this sigma Fa, sorry, sigma Fy at point A also must be 0. Okay, now see the next equation. The next equation which we can use is net force in X direction 0. And you can see that in X direction, only two forces we are left with. So they should be same. That means sigma Fx at point B should be equal to sigma Fx at point A. Right? Okay. Now see the rod AB. For rod AB, you don't have vertical forces because they have to be 0 for equilibrium. So now we have only forces Fx and Fy. So if I show it again, I'll just copy it here so that I will save the time. Okay, now see that this is 0. So let us just delete it. This is 0. This is 0. Okay. So for equilibrium, this is how the force should be. This is how the force should be. This is how the force should be. Now, see, don't misinterpret it. Don't say that, so the forces should be in X direction only, or the forces should be along the AB only. No, forces still can be like this. Forces can be like this. And see, the net force in Y direction must be 0 at point B and point B. Net force in Y direction must be 0. So you can have still number of forces, but their net perpendicular to the rod must be 0. And you see that the load which you see here, this load is nothing but the axial load. This load is nothing but the axial load. Okay. Now, what is my point? My point is, you see that if you take a straight rod, then if you apply the loads at the ends only, then that rod will experience only axial load. That rod will experience only axial load. Okay, next point. Okay, now if the rod is experiencing axial load, listen carefully. In that case only, the free body diagram can be drawn. Free body diagram can be drawn at the joint. The free body diagram can be drawn at the joint. So free body diagram at the joint can be drawn only when the body is experiencing the axial load. Okay, now the question is, what if not? That means if loading is not just axial, or it is complicated loading, shear, bending, then in that case what we have to do is simple thing is you draw the free body diagram of entire member. You draw the free body diagram of entire member. Okay, drawing the free body diagram of entire member is applicable for all the loads. Even if the load is axial, you can still go for the entire member. That will give you correct answer. But for axial load, the simplest way to solve the numericals is to draw the free body diagram at the joint. How to decide the loading is axial or not? See, this is the point here. That rod should be straight and the load should be at the ends only. I will give you example here. Keep listening. Okay. Okay, now see here. If I take a beam, if I support like this at the left end, if I support like this at the right end, this beam is called as what? This beam is called as simply supported beam, SSB. And suppose if I apply load like this, let us say this is A, let us say this is B. Now you first tell me this AB is axially loaded or not with explanation. I am waiting for your replies. AB is axially loaded or not? Give me explanation. See, again you are giving me yes or no, but yes or no don't make sense. They don't make sense. Okay, now again, that is not the explanation. That force is perpendicular. No, that is not the explanation. No. You are taking it wrong in another way. See that. How to compare that? You just look at this. The rod should be straight and the load should be at the ends. This rod is straight. Okay, first condition satisfied. But loads are not at the ends, right? One load is in between. There is this reaction. Right? And you have one more load which is not passing to the center, this external load. Right? So all loads are not passing through the end. So see that all loads are not at joints, are not at ends. As these loads are not at the ends, this is not axial loading, or not just axial loading, not just axial loading. Okay, so as this is not axial loading, don't draw free body diagram at joint. If we don't have to draw the free body diagram at the joint, then we have to draw the free body diagram of member. Free body diagram of member. So what is the member here? Member is AB. And what are the free body diagram? Then RA, RB, and P. These numericals you saw in SFD BMD. You have seen this, right? In SFD BMD, have you ever drawn free body diagram for a joint? Have you ever done that? Never. Why not? Because the members are experiencing shear force and bending moment, which is not axial loading. If it is axial loading, you can go for a joint. This is not axial loading. This is not axial loading. Okay. Okay. So you'll see these things again. Okay. Now it is time for the break. There will be break always. Okay. Yeah. 3.5 hours continuous is not possible for me. It is 7:20. We'll have 20 minutes break. So we'll meet at 7:40 around. We'll meet at 7:40. Okay, Rajendra is asking to solve numericals based upon this. Yes, we are preparing for it. We are preparing for it. We will solve lots of numerical based upon this. Hello. Hello. Can you confirm my voice is audible to you? Can you confirm it? Yes. Yes. Right. Okay. Now the first doubt. What about the WhatsApp group? WhatsApp group is created. WhatsApp group is created. How should I share the link to you? Just give me a moment. I'll just pause screen for a second. Just a second. I have paused the screen. Okay. So don't panic. I'm just copying the link of the group. Copy link. Okay. And okay. Now I'm answering this to one of the student. Okay. Now I have answered the link to one of the students, so I'm sure it is visible to everyone. You click it and you will join their group. Okay. I will add that link in the notes also. So in case if you have missed, you will find it in the notes, today's notes. Okay. Yeah, that point. Okay. Now one more thing. Yeah, this is after the break, and like we say that we'll discuss something after the break every day. Okay. Okay. Now this point, the today's point is about the revision after the class. Listen carefully. Listen carefully. Okay. Okay. Now today's title of the discussion is revision after the class. Now see our class, official class will be over by 9 p.m. but our doubts will go on. Okay. And doubts will go up to 9:30, makes it that also. Okay. So whenever you leave the class, you want to attend the doubt clearing session, you are welcome. So whenever you leave the class, whenever the class ends for you, after you get out of this Zoom meeting, this class, what you have to do is listen carefully. After that, for next 10 minutes, you don't get into anything. For example, IPL match, don't get into that. For example, some news on the TV, don't get into that. Don't talk to anyone. Don't get into anything else. What you do for these 10 minutes, you write down on paper, don't just recall, don't play in the game, in the mind only. Just write down whatever you can recall from the class. Whatever. For example, today's class, equilibrium of three forces, how three forces should be. Then the Lami's theorem. Then something about axial load we just talked about. Okay. So whatever you can recall from the class, you write it down. Write down. Okay. Now, after you are done with the writing down, suppose you are not able to recall anything more, or suppose you are able to recall some part of it. For example, Lami's theorem, you couldn't recall the entire theorem, you just recall some part of it. Okay, but you don't have reference, right? Because right after the class, it will take me some time, 1 or 2 hours to upload the notes. So whenever the notes are uploaded, you cross-check these things. Okay. Now this is the way your mind will retain most from the class. This will be the revision. Today's revision will be directly done. Okay. So what you have to do after every class, not only mechanics, every subject, every day, once you are done with the class, for next 10 minutes, right after the class, you write down whatever you can recall from the class. Believe me, I have lots of students who say to me that, sir, after practicing, I can recall, I can write each and everything from the class right after the class. Now understand the level of concentration, or understand the level of recalling they have. Okay. And this is one of the way to remember the things. You will remember it for very, very long time. Okay. So starting from today, you do it. Okay. So 10 minutes every day after class, you will write whatever you can recall from the class. And once the notes are uploaded, you will cross-check them. Okay. What more you can add here is that, suppose you want to write the things from today. Okay. Suppose you want to recall something from the yesterday, you are also welcome to do that. More recalling, more will be your memory, right? So you can do that also. You can recall something from the yesterday also. Okay, now let me add something to this. See, for revision, there is revision plan on the website already. There is a file on the website where questions are there. Questions are there. Okay, I'm sure you have visited the website. Okay, on the website there is a PDF file with a revision plan. There are questions. You just open that file, read the question, answer it, your revision will be done. And the same thing is applicable available for machine learning also. So how the revision should be, that is also there. Only thing is you have to work it out. That's what I said, that whatever you require for these two subjects, mechanics and machine learning, is already available. Your job is to only study and solve the numericals. Whatever you require for this is available there. If you need anything more than that, you just drop me a message. Okay, I will make it ready. Okay. Okay, now a lot of students are asking me that, sir, this axial loading is not clear. Can you take some examples? Can you explain again? Yes, obviously, I will do that. I will explain again, and I will see it. I will take examples also, a lot of examples also. Unable to join link, don't worry about that link now, that WhatsApp link at this moment. Okay. Okay, you want to, okay, people are asking me to show that on the website, where are those folders? Okay, now see, this is our OTT platform. Okay, now see. Okay, just yeah. Okay, now you can see on the website. Okay, see, if you open that link, you will come to this web page. On this web page, you can see there are two folders. Okay, so you go to the mechanics folder. In the mechanics folder, you can see lots of files. Are there. Okay, so see, this file is a mechanics revision. So if you just open it, see, you can see lots of questions are there. So you can pick the moment and you can write about what is a vector expression, what is the direction of the moment. You can pick the couple point, you can write what is you can define it, you write the magnitude of the couple, what is the effect, how to balance it, and all. Okay, so see, it is available for other chapters also. Okay. Okay, I want, okay, come back to the syllabus. Okay, I'll just crop this a little bit. Yeah, this much is only required. Okay, now again I'm saying it that, okay, come back to the subject here. Okay, so I'm saying here that if we have straight rod and if the loads are at the ends, then the rod will experience axial force. Okay, if the rod is experiencing axial force, then we can draw the free body diagram at the joint. Then and then only. If the loading is not axial, suppose loading is bending, shear, and suppose complex axial plus shear, then in that case you shouldn't go for the joint FBD. You should go for entire member FBD. Okay, now this is just beginning. This is not the end. I'm not going to say anything more than that. No, I'm going to say everything more than that. So numericals, when I solve, in those numericals, I will make sure that you understand this thing. This is beginning. Okay, so let me go for the next point, which is the most important point in mechanics, that is a free-body diagram. This is the beginning of every answer in the mechanics. Beginning of every answer. Every answer will start with the free-body diagram. Okay. Okay. Now see the first point about the free-body diagram. Okay, on the rough paper, you write down this. You write down this one, which I'm moving. This one. What free body includes? You write down this. Write down this. Weight of the body, external forces, contact reaction, and inertia forces. Write it down. This will be reference when I draw any free body diagram, so you can have the reference. Write it down. Okay, and once you are just write down, just post it, note it down. Write it down, because you need to have a reference. Write those points on the rough paper. Done? Yes. Okay. Now listen carefully. Listen carefully. Now see, the word pre here means the word. See the. Okay. See the word pre here. Pre means what? You just draw the diagram of that body. Just one body. Pre it. Pre it from all the supports. Pre it from every support. Okay. So you just draw that body. And then what we need to study on it? Forces on it. So what forces can come? Weight, some external force on that body will have contact with some other bodies, and we know that whenever there is a contact, that contact can give us two reaction. One is normal reaction, another is a frictional force. Okay, and one more is their inertia force. Okay, inertia force will come in dynamics. Okay, so we know something like net force is equal to mass into acceleration. If net force is equal to 0 in equilibrium, then how much will be acceleration? Acceleration will be 0. If acceleration is 0, see, this inertia force is mass into acceleration. If acceleration itself is 0, then the inertia force will also become 0. Okay, now out of these forces, whichever forces are applicable, that we will show. For example, sometimes what can happen, that body is smooth, so it will not have any friction. Okay, so depending upon whichever is applicable, that we will show. Okay, I will just take this on this side. Okay, so now this all becomes irrelevant. Okay, okay, now see on the left hand side. See on the left hand side, we have a system here. Okay, in this system, we have, this is a block. Okay, the block is connected to this ceiling here. Okay, with the help of what? With the help of a member AB. Now this member AB, I will take it as a string. This is a string. Okay, string can be called as a cable, or it can be called as a wire, or it can be called as a rope, or it can be called as a thread. Okay, there is another name I'm not able to recall at this moment. Okay, no problem. Okay, so it can be string, cable, wire, rope, thread. Okay, now listen carefully. If you take a cable or a string, we can apply only tensile force it. Let me put it in words. Cable can sustain only tensile force. Only tensile force. So we can apply only tensile force on the cable. I will show you the demo here. I've made a video here. You can see here. Now see this is a cable that is like charger is there. Charging cable is there, right? Okay. Now see in the first case, you first see the video, then I'll explain it. First see the entire video, then I'll play it again, and then I'll explain it. Okay, now see from the beginning. Now there is cable, and now see that I am pulling the ends of the cable away. So as I'm pulling the ends away, I'm applying the tension. And you see that the cable is not moving now. Cable is at equilibrium. So that cable is sustaining the tension. Okay. Next one. Now suppose I apply the compressive force. I'm bringing both ends together. So I'm applying the compressive force. But see the cable is moving. So cable is not able to sustain that. So cable can't take compressive force. Okay. Now see the next loading. Now see, I'm twisting it. I'm trying to twist it. So when I'm twisting it, see again it is moving. Again it is moving. So torsion also it can't take. Compression it can't take. Torsion it can't take. Bending also it won't take, because bending is tension plus compression. So compression it can't take. Okay. Now I can explain this with the help of motorcycle also. If you want me to do that, just ask me in the doubt clearing session. I will do it there. Point is this point that the cable can take only tension. You can't apply any other force on the cable. Okay. One more thing. Listen carefully. This tensile force is axial force. Tensile force is axial force. Okay. And when the axial force comes in the body, whenever there is a straight member and the member is loaded at the ends, we just saw that here. Okay, so see this cable, AB cable is a straight member. It is not inclined, it can't be. It is not L-shaped or another shape, it can't be. And see the loads where they are applied. Loads are applied at A and at B, because at B reaction will come, and these both loads are at the ends only. That is why this string will experience only tensile force. Okay, now let us draw the free body diagrams. So whichever bodies are there, for every body we can draw the free body diagram. So let us start with the first of them. So I'm starting with the free body diagram of the block. Keep listening, don't do anything. Okay, now see that the block is there. So free body means you first to draw the body or the block. So this is the block there. Okay, now you have the paper with you. On the paper you have written some things, right? So the first thing to show in the free body diagram is the weight of the body. Now listen carefully, weight will be vertically downward, weight will pass to center of gravity. So see, this is how the weight should be shown. Vertical downward, passing to the center of gravity. Okay, that is the first point. Okay, what is the next on the list? Next is external force on the body. Now see the main diagram. In the main diagram, we don't have any force acting on the body. See, this is not a force, this is just arrow to show, to call it as a block. Okay, so there's no force, so that second point is not applicable here. What is the third point? Third point is a support reaction. Now see that this body has contact with this string member here. So the string member will give some force, and we know the string gives tensile force. Okay, or you take it like this, that see the weight has to be balanced by the string tension, because there is no one else to balance the weight. So the weight will be balanced by the string tension. As the weight is acting downward, the string tension must be acting upward. I will take string tension as T. This is at point A. Now this entire system is in equilibrium. The entire system is in equilibrium. So if I use the equilibrium equation, which is sigma Fy is equal to 0, so what we will get is this string tension is equal to W. Okay, so how many forces are there on the block? Two forces. Which two forces? Weight of the block and string tension. How two forces can be in equilibrium? Equal, opposite, and collinear. Now see that both forces are equal, opposite, and collinear. So everything is being satisfied, right? Okay, so whatever we are discussing is consistent with the previous discussions also. Okay, now this is all about the block. This is all about the block. Okay, let us go for the next one. Let's go for the next point. Okay, now if we go for the string, so we'll go for now free body diagram of string. Okay, now listen carefully. Listen carefully. Okay, now string is a vertical member. I'll take same color, green color. Okay, now I'll name it the same way. This is B, this is A. Okay, so this is end A, this is end B. Okay, now listen carefully. Now see, from the previous free body diagram, this string tension is acting upward at point A for the block FBD. For the block FBD. So if I show the same string tension here, that should be equal and opposite. So now this will be acting downward. I'll make a note here. This is equal and opposite. Now the question is why? Okay, now answer is very simple. Now listen carefully. Now see, you are sitting on a chair mostly, right? So you are sitting on a chair. So on the top of the chair, your weight is acting. Your weight is acting. So for for you, your weight is acting downward. For you, the reaction from the top of the chair is upward. Then only your weight is balanced, and then only you are in equilibrium position. Okay, so for you, the chair reaction is upward, but for chair, that reaction must be downward because chair is being pushed downward because of your weight. So for chair, that reaction is downward. For you, the reaction is upward. That is because equal and opposite. So see again, for the block S was upward. So for the string, it will be downward. Okay. Now it is equal and opposite. So this must be same as the previous S, and the previous S was equal to W. So this will also be equal to W. Now question is, who will balance it? See, at point B, there is a ceiling. So that ceiling will give some reaction, right? So there will be some reaction at the ceiling. So this will be reaction at this ceiling, and the reaction should be equal to string tension to balance it. So this reaction will also be equal to W. Now this is the free body diagram. This is the free body diagram for the string. Okay, I'll continue here. Okay, keep listening. Now we know that there is a member, AB member. AB member is experiencing axial force. As AB member is experiencing axial force, we know that we can draw the free body diagram at the joints. And what joints are there? Joint A and joint B are there. Okay, so I will draw free body diagram for them. Listen, keep listening. So if I go for joint A, see, for the joint A means I should take only that joint, which is A. Now see, for joint A, the weight W is acting downward. Then the string tension will be acting upward. String tension, which will be same as W. If I do the same thing for joint B, for the joint B, then see, for the joint B, this is the joint B. For joint B, the reaction is acting upward. Reaction R, which is equal to string tension, which is equal to W acting downward, and the string tension will be acting downward. It will be pulling it down. So this is string tension, which will be also equal to W. Okay, now see that this is all free body diagrams together. Just let me. Okay, now see, all the free body diagrams are in front of you. All the free body diagrams are in front of you. Okay, now let's keep listening. Now see that if we go for the joint, see that this string tension is acting upward, but this string tension is acting downward. And this is always a confusion, that which way the string tension should be shown. This is always a confusion. Okay, I will give you the simplest way to remember it. The simplest way: tension in any member. Tension, if you want to show at any end, tension at any end should be shown towards other end. I'll first explain this. Listen carefully. Now listen carefully. Now see, if I want to show the tension at point A, what is the other point? Other point is point B, because AB is the member experiencing tension. Okay, so if I want to show at A, the other end is B, so I should show it towards B. If I want to show at B, the other end is A, so I should show it towards A, like this. This will be the simplest way to remember how to show the tension. So in the coming numericals, we will follow this strategy, we'll practice this strategy. So on the rough paper, again, you write down this last statement: tension at any end should be shown towards the other end. And once you are done, post next point. Yes, it is called as chord also. Thank you. It is called as chord also. I couldn't recall at that time. This is called as a chord also. If there's any other name, you can explain. Okay, write it down and just post next point. Yes, next point, right? Okay. Okay, now with all this data, I will just delete this. Okay, I'll bring this diagram again. I'll put it here. Okay, now see what I will do now. Okay, what we did up to now is we went for individual objects, like that block we went for, that string we went for, joints we went for. Now I want to show everything together. I want to show everything together. So see, if I show everything together, all the forces together. So what I will call it as, see, I'm going to call this as total system free body diagram. Total system free body means what? I am considering the every part of the system as it is given to me, as whatever the way the system is, and for that entire system, I'm going to draw the free body diagram for entire system. I'm not going to draw the free body diagram for individual body. I'm studying it here. I'm studying it here. Okay. Now, if I'm considering all the parts together, not individual parts together, now see the forces. See the way the forces will come. Okay. Now see there is a weight W. This weight will come. Now see at joint A, the string tension should be shown upward. Okay. At joint B, the string tension should be shown downward. And at joint B, we will have this support reaction, which is R. Okay. Now see the values. This string tension is equal to W. This string tension is also equal to W. This reaction is also equal to W, which makes more sense. Okay. Now see the next point. See the next point. Okay. Now I will copy this again. Now listen carefully. Okay. Now focus on this two. See this one and this one. Okay. So see these two string tensions. Tension is internal force. Tension, compression, shear, bending, twisting, all are internal forces. This is internal force experienced by the object. So these two string tensions, they are opposite, collinear, they are equal. So they will cancel each other. They will cancel each other. So as they cancel each other, they will not come in any calculation, because they are canceling each other. So if they are not coming in any calculation, I can simply take them out. They're just cancel each other, right? Okay. Now see that this whatever remaining is my total system free body diagram. This whatever is remaining is the total system free body diagram. Okay. Now see, I will give the points here. Okay. Now see here. Okay, now see this image. Okay, see that total system free body diagram. What does it include? It includes weights of the bodies, because there are lots of bodies. We are considering a total system, not one individual body. Then whatever external forces, support reactions, the end support reactions, not in between, end support. Okay, and inertia force. What it doesn't include any internal force like a string tension and all. And why it doesn't include any internal force? Because this internal forces cancel each other. Because internal forces cancel each other. Okay, now on the rough paper again, you write down this thing of the total system free body diagram. This one, which I am putting inside the box. For total system free body diagram, whatever this thing we just discussed now, you write down this on the rough paper. And once you are done, post next point, we'll go for the next point. And this is a beginning. This is a beginning. This is not the end. Every numerical which we are going to solve, we are going to use every concept we are discussing here. We are done with all the concepts. We just have to practice them for n number of numericals. Okay. Now write down this, and post next point. So on the rough paper, you must have the things for the free body diagram, things for the tension direction and the thing for the total system free body diagram. Write down them. Write down them. So that when I solve a numerical, you should have a reference that which points are taken, which points are not taken. Okay, you should have that point. Yes, now, okay. We are done with all required concepts. Now is the time for the numericals. I'm starting with the first simple numerical here. Okay, I know it is very, very simple. I want you to focus, still focus it, because don't miss anything. Don't miss anything. Okay, now we have two blocks. One block is on the other block. So let us draw the free body diagrams. Okay, now let us start with. Okay, so let us start with the free body diagram of W1. Listen, don't do anything, because I want you to listen everything. Okay, there might be some things new to you or some conceptual things might come to you. Okay, so you first draw W1. We are doing individual, not the total system. Total system also will go, but first we start with the individual. So see for W1, now see the list you have written for free body and what things are there. The first thing comes is the weight of the body. So weight here is W1. Okay, what is next? External force on the body. There is no external force here. Okay, what next? The support reactions. So see that support reaction, there is a support. The support is here. Right. So this support will give reactions. And what kind of reactions a support can give are normal reactions and friction force. Here, friction is not required. There is no movement parallel to the contact surface. So friction is not required here. Only normal reaction is required here. Now see that normal reaction on W1 by W2 will be upward. This will be upward. I will just call it as N1. N1. So on W1, the normal reaction from W2 will be upward. Okay, now understand that this value must be equal to W1 so that the system will be in equilibrium. Okay, now listen carefully. Now see the normal reaction is internal force. That will be equal and opposite on another thing. That means if we go for W2, this normal reaction will be equal and opposite. So if you go for free body diagram of W2, free body diagram of the W2. I'll just try to another color. Now see the forces here. Again, you have the piece of things written. So first is W2, no external load here. Now the support reactions, there are two supports. One is at the ground, another is at the top. At the top, we will have that N1 acting downward. N1 acting downward. N1, show it N1. Don't write it W1 directly. Don't write it. Even if that value is equal to W1, don't write it directly. There will be examples where this normal reaction will be other than W. I'm going to take those examples also. So don't write it directly. Don't write it directly that it is W1. Always write N1. There will be cases when W1 will be wrong, but there won't be any case where N1 will be wrong. Okay. Now for the W2, there is support at the ground also. So ground will also give reaction, and the ground reaction will be normal reaction. Friction is not required here. So let us call this as N2. N I'm using because these are the normal reactions. So this will be N2 here. Now see the value. Now see N2 has to balance W2 and N1. N1 is equal to W1. So, so this N2 will be equal to W1 plus W2. Okay. 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 Now this is about individual free body diagrams. Now let us go for the total system free body diagram. Now you have written something about the total system free body diagram. Read it once. Read it. Total system free body diagram. Read it once. Okay, so in total system free body diagram, we need total system. So total system includes both the blocks. So these are those blocks What it includes weights. So the two weights together, this is W1 here, and then there is W2. Okay, then what is their support reactions? Now see which support, and external loads are not here. End supports. End supports means what? See, this is the end support here, the ground one. So ground will give you the end support, and that end support here is giving the reaction N2. No inertia force, no movement here, no acceleration, and no internal force won't be here because it is going to get cancelled. Internal force gets cancelled. Now see, internal force means which force? That N1. N1, you see in this diagram that this N1 is acting upward and downward at the contact surface. So it will cancel each other. So N1 is canceling each other. N1 is canceling each other, right? So N1 won't be part of any calculation. That's why it's better to not to show it. Okay. So this is total system free body diagram. And from total system free body diagram also you can see that N2 should be equal to W1 plus W2, which is same as the right hand side. So you can either refer individual body or you can refer the total system free body diagram. There will be some numericals where total system free body diagram will be a lot easier as compared to individual. How to do that or how to find it, we'll solve through the numericals. Okay, let me zoom out so you can have a look at all the things together. Inertia force will come whenever there is a body accelerating, because inertia force is mass into acceleration, right? So bodies are not accelerating here, so no inertia force will be here. Okay. Okay, let us solve a simple question based upon this. Even this simple question was asked in the GATE exam. Last year only this was asked. Okay, now read the question and try to answer it. Read the question and try to answer it. Option D, you are telling option D. See whose pre-body diagram is asked. Pre-body diagram of upper block P is asked. Yes. See that we are asked to calculate the, or we are asked to find the pre-body diagram of upper block P, not of Q. So on the upper block, what forces will act? Its weight will act downward, which will be weight of P. And from the contact surface, there will be normal reaction. And they will just call this normal reaction equal to R. Notation can be anything, right? Now see that on this upper block, weight of the lower block will not act. Na? Weight of the lower block will not act on the upper block. Now see the options. Now which one is correct one here? See, it will be option B. Okay, now see in the option A, weight is only shown, reaction is not shown. So that block without reaction will simply fall down, no? Which is wrong. That is option A is wrong. In option C and D, the weight of Q is also shown. But why the weight of lower body will act through the upper body, right? It is not correct, right? So this is wrong, this is wrong, this is also wrong. Only option 2 is correct, or option B is correct. Yes, option B is correct. Let's go for the next one. Very simple. This was asked last year exam, GATE exam. Okay. Okay, let us discuss this numerical. Okay, very interesting numerical here. Okay. Okay, so we have three blocks. W1, W2, and W3. Okay, out of which W1 and W3 are connected through the string here. So see, this element here is a string or cable or rope or cord or thread. Okay, and it goes over this pulley. It goes over this pulley. Now at this moment, I'm taking this as a smooth pulley. Okay. In the next chapter, friction chapter, I will discuss what will happen if I consider the rough pulleys where the friction will come. Okay, so that I will do in the next chapter. Now, at this moment, I am considering the smooth pulleys. Okay, now let us talk a little bit about the pulley. Keep listening. Okay, now see, if we take some random small pulley, okay, and for this pulley, if we show the tensions we are showing. Okay, so let us say this is T1 tension, and if there is a friction, then this tension is different, which is T2. Can you recall the formula of T1 and T2? Say formula is T1 by T2 is equal to E to the power mu theta. You have seen this formula, right? Okay. Now suppose let pulley is smooth. If we take the pulley to be smooth, then what it means the friction coefficient will be how much? Friction coefficient will be 0. If friction coefficient is 0, then e to the power 0 is 1. So we can write that T1 is equal to T2. So if the pulley is smooth, the tensions on both sides must be same. That is the meaning here, right? Okay, so see on the main diagram, if I say these points, this is A, let us say this is B, let us say this is C, let us say this is D. Now see, I'm showing the tension, and something about the tension you have written on the paper. Read that statement. Read that statement. You have written something about this tension. You have written something like that. The tension should at any end should be shown towards the other end. So see here, see, listen carefully now. See, if I show the tension at A, it should be shown towards other end is B. So at A, the tension should be shown towards B. If I show the tension at B, it should be shown towards A. Similarly, if I show the tension at C, it should be towards D. If I show the tension at D, it should be towards C. So these are the directions of string tensions. Okay, now I am going to take the string tension as, I'll take this as S. S, not T. I'm taking S as string tension. Listen carefully. Okay, now see, if I talk about tension at A and tension at C, as the pulley smooth, we just got that these both tensions are same. These both tensions are same. So if the tension at A is S, the tension at C also must be equal to S. Okay, next. Now see between these 2 points. See between point A and point B. Point A to point B, there is no pulley. So there is no friction. So again, the tensions must be same. So this tension at B also must be equal to S. This tension at D must also be equal to S. Right? Okay. Now I'll just drag this so that I can make a space there. Yes. Okay. Now let us start drawing the free-body diagrams. So we'll start with the free-body diagram of block W3, the rightmost block. Okay, so that block, if we start with that block, it is a block, its weight will act downward, which is equal to W3, and see at the top of it, the string tension is acting upward. The top of it means this point is point B, the string tension is S here, no other force, though, so this S must be equal to W3. Okay, now let's go for next FBD. Okay, now let's go for free-body diagram of W1. Okay, so see the W1 here. Okay, now see for the W1, see the forces. First, its weight, which is downward, is how much? W1, right? Okay. Now see at the top of it, on the top face of it, there is point D, which is connected through a cable there. So that string tension will act upward. That is string tension. Yes. How much is that? That is equal to W3 from the free body diagram of W3. Okay. Now this block is making contact with the W2 here. So it will give some normal reaction. The normal reaction is going to come from the downside. Let us call this normal reaction as N1. Now see carefully here that this N1 will be equal to, or the N1 plus S is equal to W3. So N1 will be equal to W1 minus S, that is nothing but W1 minus W3. So the normal reaction from the block W2 on block W1 is not equal to the weight of W1, because some part of the weight is taken by the string tension. The rest part is taken by the lower block. Okay, next one. Okay, now we'll go for the free body diagram of W2, the lower block. Okay, so it is like this. Okay, now see the forces there. It's weight downward, W2. Then from the top, don't show the weight. You show the N1, equivalent and opposite. And how much is N1? N1 is equal to W1 minus W3. Okay, this block is having contact with the ground. So the ground will give some reaction. Let us call it as N2. So now this N2 will come here. Okay, now see this N2 has to balance W2 and W1. So this will be W2 plus N1, W2 and N1, it has to balance. So if I put N1 value here, this is nothing but W1 plus W2 minus W3. This will be the value of N2. One more thing. Okay, now see from this diagram. Okay, now I'll go for the free body diagram of the pulley. Okay, the next one is free body diagram of the pulley. So pulley is a circular object. Okay, now see for the pulley, there is this rod. This rod will give some reaction like this. Some reaction will come from the ceiling. So that will simply act on this rod. So I can directly show it on the pulley. So see this reaction R will come here. What more will come here? You see that on the pulley you have these two string tensions which are acting downward at point A and C. At points A and C. So we have point A here. We have point C here. Both those string tensions were acting downward. So I can show them here like this. So this is string tension here. This is string tension here. We got their values as W3 each. Now see here, this R has to balance this W2 W3s. So what will be the value of R? Value of R will be equal to 2 times S, which will be also equal to 2 times W3. Now let me zoom out so you can see all the free body diagrams together. Yes, now see all the free body diagrams together. See all the free body diagrams together. Weight of the pulley is not mentioned in the question. It's not mentioned anywhere. That's why I'm neglecting it. Let us say it is a smooth, light pulley. How can we write W3 directly? You see this block. For this block, weight is acting downward. Weight is balanced by the string tension. So they both must be same. Okay. Now let us go for the next point, which is a total system pre-board diagram. So total system pre-board diagram in which I will consider the entire system here. Right. So I will take this. Okay. It is already here. Okay, listen carefully. Now on the rough paper, you have written something about total system pre-board diagram. Read it once. Read it once. Okay. Now what comes there? Weights of all the bodies. So see, we have already 3 weights here. These 3 weights. This is W1 here. Then W3. Then W2. Okay, what more? External forces. There are no external forces here. What more? The support reactions. Now see here, these support reactions. At this point, I will have support reaction which we call as N2. There's support at the top also, so we will have this reaction R also here. What more? What more was there? No internal force now. So whatever these internal forces are here, see these internal forces, these string tensions and these normal reactions, they will cancel each other. So nothing of them will come. So this is total system pre-board diagram. Let us confirm the equilibrium. Now see that this reaction is 2 times W3, and this N2 is W1 plus W2 minus W3. So if I write them here, N2 is how much? N2 is W1 plus W2 minus W3, and this reaction was how much? Reaction was 2 times W3. Okay, now you check here that how much sigma Fy will come and post it. How much sigma Fy will come. Everything is under equilibrium. That is basic rule. Yes, it is 0. It is 0, right? Upward is equal to downward. So again, if you refer total system pre-board diagram, you will get that equal to, right? Okay. So total system pre-board diagram is extra tool with us. There will be some numericals where it will be very easy to solve the simple this total system pre-board diagram. So in numericals, I will discuss if you go for total system pre-board diagram, what will happen. Okay, all those things I will discuss. Okay. We'll go for numericals now. We'll go for next numerical now. As we'll go for this numerical. This numerical, read the question, nothing else. Just read the question. Read the question. Read the question. Read the question. Okay, now answer this question. See, we have 2 members. PR. See, this is PR and this is QR. Now these 2 members, out of these 2 members, which member is experiencing axial force and why? I'm waiting for your reply. Out of these 2 members, which member is experiencing axial force and why? I'm waiting for your replies. Explanation. I want explanation, not just answer. I don't want yes or no. No. Why? That is more important to me. Give me wrong answer with explanation, I will accept it. You should know how to decide that. How do we decide that? 2 conditions are required. One is rod should be straight, and second one is loads should be at the ends. Right? So see both the rods. If you take PR rod, if you take this PR rod, for PR rod, It is straight. QR is also straight. And if you see the loads are at R or at P. What load will come at P? At P, hinge reaction. No, it is a pin support, hinge reaction, right? So for member PR, loads are at P or are at, so are at R. So it means the loads are at the ends. Same stories for QR also. So these both members, see, these both members are axially loaded. As these members are axially loaded, now we can go for the free body diagram at joint. We can go for the free body diagram at the joint. Okay, so that is why we will go for the free body diagram at this joint. Or keep listening, don't do anything, don't write, don't do anything. Okay, so we are going for the free body diagram at joint R. Okay, listen, keep listening. Okay, now at joint R, if I take this point as joint R, the weight W is acting downward. Weight W is acting downward, right? Okay, now there are two members, PR and QR. PR and QR, which are connected at R, both are axially loaded, which is confirmed. Now imagine that axial loaded can be tension or compression, right? Axial tension is also axial loaded, compression is also axial loaded. Now what we will do while solving the numericals, we will assume tension. Listen carefully. Axial loaded is confirmed, tension compression is not confirmed. So don't do any further analysis that whether it's tension or not. Don't do something like that W will pull both the down, so both are under tension. You don't have to, because it's very simple, anyone can do this. But if I give you complicated numerical, it will be very difficult. You don't have to do that. What you simply have to do is you have to assume tension. If the result comes positive as assumed as assumption, then tension is correct. If result comes negative, then it is compression. Very simple, no need to stretch your mind, right? Okay, so we will assume tension. Now we just saw that tension, or you're written on the paper also, that the tension should be shown towards the other end. So if I want to show the tension at point R in the member PR, I should show it towards P, towards other end. If I show for the member QR, it should be shown towards Q. So see how I will name this. Tension as, this is in member QR, so this is SQR. This is again tension in the member PR, so this is SPR. So if I show those two here, it will be like this. So let's see. So these are SQR and this is SPR. Let us see the angles. Okay, now see, the angles are given here in the main diagram. Okay, see, this is alpha given and this is beta given. Now don't ever lose your contact from what is asked. What is asked to you is force in the member QR. So we need only QR. We need only QR, right? So we can go for the Lami's theorem. We can only write the ratio for QR in terms of W. So we don't have to go for PR. No need to write it at all, right? So we'll do that only. So we need SQR. So we'll start with SQR. SQR divided by, now see which angle we need. We need this angle. This will be what? This will be 180 minus alpha, right? So SQR divided by sine 180 minus alpha is equal to W divided by, what is the opposite angle here? You can say, or you can say that it is alpha plus beta. So this is sine alpha plus beta. Okay, sine 180 minus alpha is sine alpha. So from here I can write that SQR is equal to W into sine alpha divided by sine of alpha plus beta. So where is that answer? I think it is option B. Okay, now see all the things. Now see all the things. Okay, see, not just answer. Everything should be understood. Everything should be understood, not just the answer. Okay. Okay, see this numerical, if you have seen anywhere else, that faculty will directly draw the free body diagram at joint, but he will never explain that means when not to draw the free body diagram at the joint. Okay, so that point will be always unanswered. Okay. Okay, let's go for next numerical. Okay, now you first read the question. You have to read the question and you have to answer me this, that see in the question a member ACB is mentioned. Is here, is this one. So this ACB are not two members, it is a one member mentioned in the first line itself, right? So you have to tell me that this member ACB is subjected to axial loading or not, with explanation. Read the question and give me that answer. Mitra, I want an explanation. Explanation. Good, Sachin. Are in good. Yes, very good. Okay, now see, both things it is not satisfying. What are the both things? What are the two things? The member should be straight and the member should have forces at the ends, which both are not satisfied here. Both are not satisfied now. Okay, so I'm convinced that it is not axially loaded. Okay, now if it is not axially loaded, can we draw the free body diagram of the joint? No, because it is not axially loaded. If we can't draw the free body diagram at the joint, then what we should do is we should go for the free body diagram of a member. See, this is what is the doubt, which is not even like discussed. You see the solutions, the teacher will directly draw the free body diagram sometimes for the member and sometimes for the joint, and he will never even say that when to go for member and when to go for joint. That's what I was saying, that this doubt don't even come to students' mind, not even to teachers' mind, that when to go for member and when to go for joint. That's what is totally addressed here, right? Okay, so we should go for the joint, not for the member, so the member, we should go for the member, not for the joint. Okay, slip of the tongue. Okay, so we should go for the member. Okay, so see, the member is like this. Don't solve, just go with me. Don't solve. So it is something like this. I will draw it like this. So this is the ACB member. Keep listening. No, nothing you do other than listening. Okay, this is A here. Okay, now loads. This is a P, external one. Then there will be support reactions. Look at B. At B, it is a roller. So one reaction perpendicular to the support of roller. Support of the roller is vertical. So the reaction at B will be horizontal. Okay. This is named as RBH. Then see at A. At A, you can see one pin here. See the pin here. That circle is a pin. Pin is a pin joint. Pin joint is a hinge joint. Hinge joint gives two reactions. So I will have two reactions here. Two reactions, vertical, horizontal, we can show. Directions and directions. You just assume and directions, right, left, as per your convention. And see how they are named. These are named as RAH and RA vertical. Don't write. Okay. Now see what most of you will do is this. You will do that. How many forces are here? Four forces. Which four forces? RBH, P, RAV, and REH. Okay. So out of these four forces, how many unknowns? Three reactions are unknown. Three reactions are unknown. How? Okay. I'll write it here. I will write. So what are the unknowns here? Unknowns are RBH, RAH, RA vertical. Okay. What are the equations? Which equations we can use? See, we have forces in XY plane, right? So as the forces are in XY plane, we can use sigma fx0. We can use sigma fy0, and we can use moment 0 also. Okay. So what thing will come to most of your mind, most of you is three equations, three unknowns, right? Three equations, solve them, you get three unknowns. But that is not the competitive exams approach, not at all. You have to solve it differently. See the way I will solve this. I won't go for all the equations. I will simply go for only one equation, and the equation which I will go for is sigma fx0. Now see the diagram. Diagram tells me that RBH towards left hand side. So minus RBH plus RAH should be equal to 0. It also tells me that this RBH should be equal to RAH. Now again I'm telling you that whenever you write any equation or you get any value, check options. Check options. Now options are in front of you. Now tell me in how many options you have RAH equal to RBH. You only tell me in how many options. There's only one option, and that must be the answer, right? So we have the winner here. The answer is option B. The answer is option A. Now why do you want to go for rest of the things, right? Okay, even if you do that, you will get the same answer, right? You will get the same answer, but point is not to go for. Understand this approach in my class also. Miss what way I am solving the numericals. Okay, even if we solve, we'll get those values, but not required to get there. Okay. Okay, I'm sure that you don't want me to solve it, right? Right, because we can go for more numericals. Okay. Okay. Okay, we'll go for next one. We'll go for this question. Okay, now listen carefully. What you have to do is read this question and try to draw the diagram. Try to draw the diagram. Try to draw the diagram based upon the data mentioned in the question. Try to draw the diagram. This was asked in ESE exam 2017. Very simple question it was. Okay, and you don't have calculator. Even if you try solving it, don't use a calculator at all. You don't have it. You don't need it. Okay, listen carefully. Listen carefully. You must have come across a very good number of questions of the mechanics. Okay, you go for interview or you tell someone that you are a mechanical engineer or you're studying mechanical engineer. Then the next person will try to ask you a question from mechanics, right? And what happens whenever you come across some tricky questions, some interesting questions of the mechanics, and you're not getting the answer, which is understandable. When you see the answer, the thought comes to your mind that I could have done it. I could have done it. If I had thought like that, I would have got the answer. So it is like a puzzles, solving puzzles. So when you see a puzzle, you find that it's the most difficult puzzle in the world. You see the answer and you will think that I could have solved it. Same thing is for mechanics also. That you see a question, you will find it is the most difficult question in the world. It is like $1 million question. You see the answer and you will think I could have done it. Now the gap between it is $1 million question and I could have done it, that gap can be bridged by practicing. Practicing means making the mistakes. So that is why I specially asked you to draw the diagram here. I asked you to, okay, so draw the diagram, understand the data, and then you'll keep understanding, okay, where you might have done mistake. Okay, so see here, there is a ball. There is a ball mentioned. So ball, obviously in one we will use circle, and it is tied against a wall mentioned in the question. So there should be a wall mentioned. So see, this is a wall here. This is a wall here, right? Okay. Now there is string tied to it. You just can't keep ball like this. Ball won't be there. So there has to be string. So string is like this. Okay, so string is tied like this. Okay, and string is making how much angle? 30 degree with whom? With the wall. This angle is 30 degree with the wall. Okay, and a smooth wall, so no friction. So what forces will come here? Weight of the ball, which will act through the center, W, which is 100 Newton. Okay, now see at the contact point. At the contact point, we discussed this point that the contact point can give two reactions, normal and friction force. As smooth is mentioned here, friction won't be there. If smooth can't give friction, then what it will give? It will give the normal reaction. Okay. Now see that normal means perpendicular to the contact surface. The contact surface here is the wall. Wall is tangential to the circle. Tangential to circle, and if you draw perpendicular to tangent, it must pass through the centers. So that is why this normal reaction here must be along the center line. Okay, and then there is a string. There is a string. String will be aligned with the center. String tension, if I show, it should be shown like this. You see, at this end, it should be towards the other end, and the other end is this one. At this end, it should be towards this end. So this is string tensions. Okay, so let us say the center is O. If I show all these forces at the center, which is point O, see the forces. Weight is acting downward. Weight is acting downward, which is how much? 100 Newton. Then that normal reaction is this way, and then the string tension by transmissibility, I can show it here. String tension, see the angle. Angle is with vertical. So string tension with vertical, wall is vertical always. So this angle is 30 degrees. Okay, so we need string tension. And what are the unknowns here? String tension and the normal reaction here. So we don't need normal reaction. Normal reaction is acting horizontal. So to avoid normal reaction, I can simply use sigma Fy0. Sigma Fy0 will avoid normal reaction, which is not required. So sigma Fy0 means vertical component of S is cos component. So S cos 30 should be equal to 100. Cos 30 is root 3 by 2. So this is S into root 3 by 2 is equal to 100. Okay, I will show it here. Therefore, S will be equal to 2 into 100 is 200. 200 divided by root 3 Newton. No calculator is required. No calculator is available also. So you have option B answer here. Okay. Now again, read the question and see the things. We can use the Lami theorem also, which will give the same answer. So whichever is easy, we'll go for that. Whichever is easy, we'll go for that. Okay. Okay, now here is another homework question for you, and here we will stop today. Okay, now listen the homework question. Listen to homework question. Okay, now see the diagram. In the diagram, I am taking the string, the line of the string passing to the center, isn't it? Right? That's how I got it, the string tension here. Okay, I repeat that I'm taking the string passing to the center, but is it mentioned in the question anywhere that the string line is aligned with the center? It is not mentioned. It is not mentioned. So if it is not mentioned in the question, then still why we are taking the string line aligned with the center? So that is today's question. Question is, why string is taken aligned with center? Don't give us answers now because others want to think on it. Okay, so tomorrow when we start the class at 5:30, we'll start with this doubt. I think there's one more doubt. Yeah, there one more doubt was given to you. A homework question was given to you, right? Okay, so this will be end of today's class. Now I will start taking doubts. To ask the doubt, you have to raise the hand. I'll just allow you to raise the hand. And those who want to leave, you are welcome to leave, no problem. Like I told you that you do that 10 minutes work, right? You try to recall whatever we studied today. Okay. If you can recall those things will be printed in your mind permanently. Okay. So now I will allow you to raise the hand. Yes, you can start raising the hand to ask the doubt. Yeah, now Smurtika is the first one. Smurtika, unmute and ask the doubt.
Good evening, sir.
Good evening.
Sir, I have the doubt about the point that tension at any end should be shown towards the other end.
Yes. Yes.
Sir, like I didn't get the statement actually.
Okay. Now see these two diagrams here. Okay. See this point A here. At point A for equilibrium, this tension must be upward. At point B for equilibrium, this tension must be downward. Okay.
Yes.
If I see same point A in the main diagram, which I'm highlighting just now. Okay. So see that tension is towards B. And if I see the point B, the tension is towards A. So this gives me clear indication that the tension should be shown towards the other end.
So it is like opposite end, towards the opposite end.
Yeah, because tension will come in a member. Member will have two ends. You want to show tension at one end, show it towards the other end, like that.
Okay. Sir, another question, that FBD of pulley.
This one.
FBD of pulley.
Only a bit of the pulley. This one.
Yes. That reaction force that.
See this member, the highlighted one. So this will be some rod there, right? Hello.
Okay.
Yeah. So this rod is connected to the
sir,
ceiling.
I am here.
Rod is connected to the ceiling. So rod will have some reaction from the ceiling. That reaction will come straight to the rod, which will act on the pulley. See, there has to be someone holding the pulley. That is that rod, which is bringing in the reaction.
Yes. Okay. Got it, sir.
Okay.
Thank you.
It's welcome. Rajendra.
Good evening, sir. Am I audible?
Good evening. Yes, you're audible. Yes.
Sir, in the last question that we have solved today, since the rod so the last question, ESE 20, yes. Sir, the rod which is connecting the massed object, sir, the forces are only vertical, right?
Say your statement again.
So the forces are only action forces, right?
Which force?
On the cord which is connecting the mass.
On the cord which is connecting this ball.
Yes.
Okay.
So the condition that you have told today, that if the forces are only actually acting on the rod
Hmm.
or on a straight element, we can take the FBD about a point, right?
Yes. Yes.
Sir, but we have shifted that point towards O and then we have taken it, not exactly at the joint,
Okay.
right?
Okay. Okay. Now see that at this joint, which I just highlighted, you have two members connected. One is this string and another is this ball. String is axial loaded, no doubt, but ball is not axial loaded, right? So at this joint, you don't have both connected members axially loaded, so you shouldn't go for free body diagram of this joint. Is that okay?
Sir, but in the previous, like in the question where we have alpha and beta angles given.
In this one.
So 1 second, the screen hasn't come yet.
Yes, lag is there. Okay.
Sir, yeah, in this question, sir, it is actual for the PR link.
At
Also
joint R, both members are axially loaded, no?
Okay, but we can't. Okay, fine, got it, sir.
That is why we went for that joint. But if we come back to this numerical, at this joint, both connected members are not axially loaded. So that is why we can't go this joint.
Okay, and sir, one more, sir. The question that we have solved today, 2021 XE question.
20, just let me.
There was one. Yeah, sir. Why have like I know from the options it is sure that we'll do this process only, but for a time being remove all the options. Okay. Sir, then we also have to consider the reaction force from the support because we haven't considered it, sir.
Okay. If you consider the reaction from the upper support and if you bring that reaction to the point B, then the system will be in equilibrium.
Yeah.
Okay, system will be in equilibrium. Okay, so you'll come to know how the equilibrium is there. But if you want to know what is happening to that point B, what is happening to the area at point B, so that means you have to find what are the internal forces and how do we find internal forces? Cut it and see one side. That's the story.
Okay, but
so this
sir,
this will help you to find what are the internal forces there.
Okay, but so the question says the equivalent force couple system at B. It is asking for equivalent. That means we have to take all the forces into consideration.
See, it also means it. See, that's what I say, that if you bring reaction now, then there won't be any force at B.
Yes.
There won't be any force at B. And
yeah.
If they don't give options, then they will be more careful in that case that you find the equivalent force couple system because of 40 kN only. They will be that specific in that case.
Yeah, got it, sir. And sir, one very silly question, sir, regarding pulley.
Don't judge it, just ask it.
Yeah, sir, we have shown the forces only in two directions. Like in this pulley, we have shown it vertically down only, S and S. Sir, but the stretching would be at every point in the pulley circumference. Is in contact with
it will cancel each other. It will cancel each other. At any point you take it now, it is upward, downward, so it will cancel each other.
Okay, so effectively we will be left with only two forces.
These two end forces only, yes.
Even if we consider the mass of the pulley, sir?
Mass of the pulley, see, the mass of the pulley won't change these tensions because they are balancing the different weights. Okay, so the mass of the pulley will bring more this sealing reaction.
Okay, yeah.
Okay.
Yeah, got it. Yes, sir. Thank you very much, sir, and good night.
Sagar.
Hello, sir. I am audible.
Yes, you are audible. Yes.
Sir, I have a doubt in movement. Means you have taken means clockwise. It is a negative, no?
Yes, clockwise we take negative, that is standard, and anti-clockwise positive. That is standard.
The magnitude of it is positive means for a negative moment, it is positive value means I am confused about that means.
See, suppose if I apply
General
moment,
we take
this moment,
Hmm.
suppose it is 10 Newton meter. I will simply take it as minus because it is clockwise. Because it is clockwise.
sir.
That's-
But when the movement is means clockwise, in general we take a positive, no? Means
No,
clockwise
no, no.
is
Okay.
negative.
See, you might be talking about talking from the reference of SFD BMD. Okay.
Yes, sir.
See, that's what I've said in first point that this sign convention is for mechanics, and this is a standard sign convention in the mechanics only. But SFD BMD has a different sign conventions. What sign conventions that I shouldn't comment because whatever strength of matters faculty will say, you go with that.
Yes, sir.
This has nothing to do with SFD BMD sign conventions. If you find them similar, lucky. If you don't find them similar, we don't know what.
Sir, in starting there is question number 6 means where movement is taken.
Question.
Movement shift is there means from upward to downward.
Keep saying. Moment
Uh,
shift. Can you say something more
we have
about
to
that
shift
question?
the movement from upward to downward. Means it is coming along clockwise.
This
Movement
one.
is clockwise. Sir, here only. Sir, movement must be minus 2 pa, no?
Options are including the direction. You can see
Sir, but we have if we have to give the magnitude of it, we have to give it
yeah,
minus.
we are showing the direction, right? Minus would mean it clockwise, but we are already showing the direction, right?
If direction is not shown, so
Then there will be minus 2p.
minus 2p. Acha, okay, sir. Yes, sir. That only is the doubt means I am posting regarding that, but
Okay.
yes, sir.
See, there are. I will share that there are almost 1.5 thousand messages. It's impossible
Okay.
to go. Okay.
Yes, sir.
Okay. Yeah.
So means here, if direction is not given, we have to consider it along the sign,
Negative.
particular sign convection that is
Yes.
negative clockwise and
Yes.
positive anti-clockwise.
Yes.
Okay, sir. Okay, sir. Got it, sir. Thank you, sir.
Okay. Sri Tataya Naidu.
Yes, sir. Good evening,
Hello.
sir.
Good evening. Yeah.
Sir, could you explain the axial loading concept, sir? Like why we consider free body diagram for joints and not members? Could you explain it once?
See, okay. When the axle loading will come when you have straight member subjected to loads at the ends, and then only you should go for the free body diagram at the joint. Now I'll go on something more. See, if you have simple supported beam member is subjected to, or beam is subjected to bending and twist, bending and shear. Okay, so it is not axial loaded. So suppose if you try to draw the free body diagram at joint A, then how you will show the force in member AB? It is not axial now, so you can't show it along AB. It is bending and shear. So that will be complicated now. That is why whenever the members are not axially loaded, don't go for the joint.
Okay, sir.
Okay.
Sir, and another doubt, sir. You have given question, sir. Member is not straight. Could you go for that question, sir?
Member is not straight.
Member, I think it's second
This
from
one.
yes, this one, sir.
Yeah.
And at B you consider RBH, but
Yes.
but not RBV. Why there is no vertical reaction?
Okay. See the diagram clearly. Can you see the rollers there?
Okay, sir. Okay, fine.
A roller will give only one reaction, right?
Okay. Sir, and at starting of the session, there is a block and it is subjected to tensile load both direction P. It is in equilibrium, but the force acted on the block is P. You said you have to consider the force in half of the direction B. Could you elaborate it once?
See, this diagram only, right? So you have Okay, so something. Okay,
You said
now see.
consider from up direction only. Like
See, if you apply tensile force, the body will experience something. No? Body will
yes, sir.
experience, even if it. So
Body
how
will
much that experience that we treat it as internal force. So we have to
But
cut it and we have to
in,
see one side.
Sir, but in engineering mechanics, we consider the body is rigid, so there is we don't consider any stresses no, sir, within the
No,
system.
okay. Have you studied strength of materials?
Okay, sir. In strength of materials, the material is undergoing some deformation, so
No,
we
okay.
consider
No,
there
I'm
is
saying
stress
that.
developed within.
Okay. In strength of materials, if you go for stress strain diagram, how is the stress strain diagram for the rigid material?
Rigid material, there will be no strain.
No strain, but stress will be there, no? Like
Yes,
this.
sir. Yes.
So this is for rigid material, no?
Yes, sir.
Fluid will be along x-axis, no stress. Okay. So rigid material has a stress. Stress is not zero. Strain is zero, no?
Yes, sir. Strain is zero. Stress
So
is not
stress
zero.
is not zero means there is some internal force acting, no? Only thing is
Okay.
that rigid body can take it. Rigid body can take infinite internal force.
Okay.
Okay, so stress is there, strain is not there. This is one of the interview question that give examples where stress is non-zero but strain is zero. Rigid material. There can be other example also that where strain is zero but stress is not zero, or strain is non-zero but stress is zero. There can be another example also. Interview questions. Okay, is it clear?
Okay, sir. Okay. Thank you. Thank you, sir.
Apurva Kulkarni.
Sir, can you please explain? You explained on the OTS platform that packages because my connection got disconnected. So
Which thing? Can you say it again?
OTS platform packages.
Packages.
You were something explaining about OTS platform.
Did I?
In between.
What did I explain that? Can you say something because I don't.
I was not able to connect at that time.
Okay, was I showing some files there? Maybe something like that.
Maybe.
Okay, maybe. Okay, because you couldn't get it. See, I was showing
my connection got disconnected. That's
okay.
why.
Actually, I was showing this. Okay, I was showing.
Yes, this something.
Yeah, I was showing this website which I maintain.
Okay.
And where you can get all the files.
That
like
drive link. Okay.
The drive link. That is day one yesterday. So today also it will be uploaded. I was saying that. Other than this, I don't think I was talking about anything. Okay.
Okay. Yeah. Thank you, sir.
Yes. Sudeep.
Hello, sir.
Hello.
Sir, in that pulley problem, 3 marks.
Just a second. Sudeep, the students are asking for the link, so I'll just copy it and I will give to them. I'm posting my link to one of the answers, so it is visible to everyone, so you can see that. You can directly click it. Okay. Yeah. So you come back to your question. Yeah.
Yes, sir. In that problem, if we take total system FBD, okay.
Which problem?
In the pulley and 3-block system.
Pulley and 3-block system. This one.
Yes, sir. Sir, if we draw in total system FBD, then should we consider W1, W2, and W3 also?
We have considered these are external weights. No one cancels them. Only thing we don't consider is the internal force. Why we don't consider internal force? Because the internal force gets cancelled. It is equal and opposite. That is why only that is not considered. That is not required to be considered.
So, sir, if we write summation Fy, then R is there, and if we take W1, W2, and W3, okay. So there is extra term that is N2 also, no?
See on the rough paper, total system includes the end support reactions also, right? So we have end supports at the ground and at the top, no?
Okay.
So those reactions will also be there. No?
तो सर हिंदी में बोलता हूँ सर. सर ये R और जो N2 है ये दोनों कैंसिल कर जाएगा ना?
See, no one is to cancel it because they are end supports. No? They are end supports. You read what you read on wrote on the paper that pre-body total system pre-body includes the end support reactions also. So these are the
Yes.
end supports reactions.
Okay. अच्छा ठीक है सर.
Okay.
ठीक है सर. Thank you.
Punnaya Sastri. I hope I'm.
Yes, sir. Good evening, sir.
Correct. Yes. Good evening.
Sir, in the question what you are displaying, there if W3 is greater than W1, system will accelerate.
Yes, in that case, system will accelerate because W3 will pull W1 up.
Yes, sir. So W1 rate of W1 should be either greater than or equal to W3. No, sir.
Yes, it should. That should be there. I should have mentioned that, but I miss by default we take equilibrium.
Yes, sir.
Yeah.
For equilibrium, that condition should be satisfied.
Yes, it should be satisfied. W3 should be less than W1.
Sir, can you go to the axial loading condition? Sir, you expand that.
Yes.
Sir, here, what about the sigma Fi, sir? Why is it going to be 0?
Because for equilibrium, no? If you take moment at A, sigma Fi at B will become 0. If you take moment at B, sigma Fi at A has to be 0 for equilibrium.
Yes, sir.
Otherwise, it will create moment. Moment is not equilibrium, right?
Yes, sir. Sir, and in a question, there is loaded series, sir. We took a beating of a section. Just last second problem from last solver. Yes, this question, sir. Sir, as sir, here you showed that this is a roller support. Support is
this one or
not, sir. Previous question, sir.
This
you showed
one.
Me first. Not, sir. You showed me first question. Yes, sir. This one, sir. In this, at B, it is roller support.
See, it is mentioned in the question also. See, it is mentioned in the question. That's why I insist on reading the question. See, roller is mentioned.
Sir, what my doubt is, system slide down, sir, because it is roller support.
But this is A there, no? A is a pin support. It will stop, no? It will stop the system from coming down, no?
Yes, sir.
A will hold it.
Okay, sir. That's it, sir. Thanks.
Yeah. Yes.
What's that, sir? What are the homework questions today, sir? You said that 2 are there. At one.
This is one question, that Y string should be aligned with this center, and the another homework question is this question, that you find the components of this 100 Newton along OX and OY lines.
Yes, sir. Yes, sir.
Yeah.
Thank you, sir.
Tej Sachin Shipte.
Hello.
Are you there? Hello. Hello. Yeah.
So, can you tell me how to draw FBD for member? For member, how to draw FBD? Because I don't understand last question, second last question.
This one.
No. Second last. There are taken FBD for members.
See the screen. Is it this?
Yes, this one.
Yeah. Now, which part you didn't understand?
Sir, at A, for member A, they taken you two FBDs for RAV vertical and horizontal.
Yes.
How, sir?
So, okay. See the main diagram. A is a hinge support, no? Pin support.
Okay.
Pin means hinge only, na.
Okay.
So hinge support gives you two reactions. So these are two reactions of the hinge support.
Okay. Okay.
Okay.
And for roller support.
Roller give only one reaction.
Okay. But how
Roller
to
gives.
decide if the horizontal or vertical?
Okay. Okay.
For roller
See,
support.
okay. Now see, for roller, the reaction is perpendicular to the surface of the roller. And see, the surface of the roller is vertical. Na? See, rollers are like this. This is the support of the roller.
Okay.
So the reaction is always perpendicular to the surface on which rollers are kept.
Okay. Okay.
Here that support is vertical, so the reaction will be horizontal.
Okay. Sir, I have another doubt.
Okay.
If the tension in a spring are cancelled to each other, then it will take in calculation or not?
Okay. If you
last question, this short. Yes.
Okay. Here this question, right? Okay. Now see, suppose you take entire system. For an entire system, this string tension will cancel, na? But if you consider one of them, so you are considering this ball. For ball, only this thing is acting. This is acting. This S is not acting on the ball. So no one is to cancel this S there, or the cancelling S is not on the ball. So if you talk about the ball, you have to show the string tension. But if you consider the entire system, in the entire system, this both S will cancel each other. So you don't have to show it there.
Okay. Okay. And sir, at
see, miss, it is. I totally understand this is not clear at this moment, but more numericals are coming. Okay, so just have this doubt in the mind that when to show the tension and when not to show the tension. Have doubts and you will see the answers.
Okay. Okay.
Okay.
So another question. At the actual load, there at actual diagram.
Which question?
There actual loading.
Actual loading.
Sir, how there you how to get the loads?
No, loads we can apply. That is we can apply any number of loads at the ends. Any number, 1, 2, 3, 10, 20, any number of loads, any directions. But no matter what you do, yes, any direction. Even means this P3 you can take it like this. But as I have written the equation, I will just hold it vertical only.
At main diagram below, there is two loads are shown.
Yeah, sigma fx and sigma fy. So whatever forces were acting at B. See, we have three forces here at B, right? So I just took their resultants along X and Y, and I've shown them. So both are same, right? Either you show n number of forces or show their components.
Okay. Thank you, sir.
Yes. Tarun.
Good evening, sir.
Good evening.
Sir, I have a doubt in couple.
Yes.
Yesterday's concept.
It is on the screen.
Yes, sir. If two forces are couples are equal in magnitude, act on a rod, sir.
Yeah.
They acted on one side of the from mid, sir, from mid of the rod. Then about what point the body will rotate, sir?
Okay, your question is something like this. Suppose this is a rod. Suppose one force is here and another force is here.
Yes, sir.
Right. So your question is about which point it will rotate. Okay.
Yes, sir.
Okay. Now see that if you apply forces like this, and suppose means you are not restricting it, it can rotate under. So in that case, now it is most likely to rotate about center because moment of inertia is minimum at the center. So it is most likely to rotate about the center. Okay.
Okay.
Someone Janki. Someone with name Janki, are you there? Okay, no reply. Okay. Akhil.
Hello, sir.
Akhil.
Sir, I just have a small doubt. Like for moment, how we are doing that anti-clockwise clockwise thing, sir? Like if you apply moment, there was one question where you took all the forces and applied on point A.
This one.
Yes, sir. Like how you got this clockwise when you took point from C and you put it on A, how you got clockwise?
Okay, I will. Okay, look at the. Okay. See this force at B.
Yes, sir.
And point A. Okay. Now you imagine your right hand. Okay.
Yes, sir.
Now right hand का जो fist क्या बोलते हैं उसको palm of the right hand. Okay.
Okay.
So you take it from A to B. So you take fingers towards B of right hand. Okay. From A to B. Okay. Then you see the forces towards right hand side. So now turn your fingers towards right hand side because forces towards right hand side. Okay.
Okay, sir.
Now see those fingers are turning clockwise, right?
Okay, sir. Like, but if you apply the force on A, then it will be from anti-clockwise, no, sir. Like you took the force from C and put it on A, so you're applying on point A. So then it should be.
See, I'm not balancing it. I'm just shifting it. Shift it. You are not asked to balance it. You are asked to shift it.
Okay, sir. The direction will be different. Just you're putting the force on A.
Direction will be consistent with the direction. Means the way the moment will come, no?
Yes, sir.
Okay. So you can use right hand thumb rule to get the direction if you are getting confused. Okay.
Okay, sir. Okay.
Okay. Muram Janki, if you are there, you can unmute and ask if you are unmuted.
Hello.
Hello. Speak a little loudly.
Hello, sir.
Speak a little bit more loudly.
Good evening, sir.
Good evening.
I have a doubt in uniform varying load, sir. I didn't really understand it.
Which load?
Uniform varying load.
Uniform?
Varying load.
Which subject? Mechanics?
Sir, you are explaining starting uniform varying load, sir. UVL.
UVL. Okay. UVL.
Yes,
What is
sir.
what is your doubt there?
I didn't explain have the load distributed in uniform varying load, sir. Understand?
You didn't understand what I was talking about that, right?
Yes, sir.
Okay. Now suppose we have a beam. On beam, suppose our load is like this.
Okay.
So see the load is changing. So it is varying. This variation is linear, no?
Yes, sir.
That is why it is uniformly varying load.
You
Okay.
are explaining about centroid.
No, that I'm coming to. Okay. So this height is omega. This length is L. So how much is the area of the triangle? Triangle area is 1/2 omega into L.
Yes, sir.
Now that is equal to total load.
Okay.
And this total load will act at the centroid.
Okay, sir.
So centroid for the triangle is L/3 or 12/3 from ends, right?
Okay, sir. Understand, sir.
Okay.
Sir, I have a doubt that reaction forces at hinged and rolling support, sir.
Let's put the numerical. Yeah, this numerical. Yeah. Now what is your doubt here?
I know that the hinged having vertical and horizontal reactions, sir, but I didn't know this clear explanation, sir.
Okay, so just imagine a door in your home. Okay,
Yes,
so
sir.
door has hinges at the end, right? Okay, you try to apply horizontal force on the door, it won't move, right? So horizontal reaction should be there.
Okay.
You try to push that door upward, so you're applying upward force. Again, the door is not moving, so that the hinge must be given downward reaction, right?
Yes, sir.
So hinge gives you two reactions, vertical up and a horizontal.
In roller, we have having when we apply horizontal force, then it moves. Then we don't have horizontal reaction.
No, don't think like this. Think like this. Okay, see the chair on which chair. Imagine roller chair. A rolling chair can be imagined, right?
Yes.
Chair with the rollers at the bottom. So if you keep that chair on the ground, and if you apply vertical downward force, then chair won't move.
Okay.
Okay, but if you keep that chair on the wall, if you just hold it on the wall, and if you push it on the wall, it won't move. So basically, the roller support gives you a reaction which is perpendicular to the surface on which roller is kept.
Okay, sir.
Okay.
Okay, sir.
In this example, the rollers are kept on the vertical wall. That is why the reaction is horizontal.
Okay, sir. Thank you, sir.
Suraj Kumar.
Hello.
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 Sir, please explain the last problem, sir. ESE problem, sir.
This one,
Yes, sir. Tell me, sir, S cos 30, we written as instead of S cos 30, you written at sin 30, sir. How we written S cos 30, sir?
Okay, yesterday we discussed this. If
Yes,
a force
sir.
is there, if the
Yes,
force
sir.
is making angle with a line, then cos component will be along that line. So this string is making angle with vertical. So vertical component will be cos component.
Vertical means, sir, 1 second, sir, I cannot get it. That वही हमको डाउट होता है सर एक्चुअली मैं समझ में नहीं आता है तो वर्टिकल हॉरिजॉन्टल सर साइन cos में है
Okay, मैं दिखाता हूँ यहाँ पे देखो. See, this is the string tension.
Yes, sir.
The angle made by this string tension with vertical is 30.
Yes, sir.
We can take its two components. One will be this and one
Yes,
will
sir.
be this.
Yes, sir.
Now see that this is going to be cos component because the angle made with this is 30 degrees. That is why this is cos component. And then this will be sine component.
Okay.
Angle made with line, that line will have cos component.
Okay.
Okay.
Sir, a freeboard diagram, sir. Problem on the freeboard diagram. Please explain that.
Which problem? Can you describe the
The
problem?
first problem you have done, no, sir. The total SST, that one. Yes, sir. That one, sir. Yes, sir. That one only. Sir, that first was then first block. You are written W1 is downward. Then you will put normal force. Normal force हम दे रहे तो W1 होता है N1 equal W1 normal force दे रहे सर. तो सर हम लोग जो सेकंड में दिए सर W2 जो N1 इसको W1 है ना सर वो सर क्यों हुआ सर वो एक्चुअली समझ नहीं पाया.
कोई ना reaction equal and opposite होती है ना. If you push the wall, the
Yes,
reaction by the wall will be same ना.
Oh, sure.
Reaction is equal and opposite. Like you are sitting on the chair. Reaction
Yes,
on you by the chair and the reaction on the chair, they are same, but they are equal and opposite. No?
Okay. Sure. Okay, sir. Sir, first problem was there, sir. First wings 16-meter aeroplane. That problem, sir. First problem of today's class.
Just a second, we're going there. ये वाला, this one.
Sir, that one. So please again explain. Actually, I'm not getting that part. Actually.
See, means you have to find the total load. So to find the total load, you have to take a total area. So total area is small area. You have to integrate it. So that's
yes,
the
sir.
approach.
खाली इंटीग्रेशन सर किया ना आप जो 90 रूट अगर डायरेक्ट इंटीग्रेशन है सर ये वाला
90 root x is a height at any location. Height.
Okay.
That is y. So you have to integrate it.
जो सर आप जो इंटीग्रेट के x into x to power 3/2 वन ना सर बोला सर क्या कोई कैसे वो सर और एक्सप्लेन कीजिए सर और x to 3/2
okay, so see, this is root x na.
yes root x
means x to the power 1/2.
x to 1/2 right.
Yeah, so x to the power n integration is what? X to the power n plus 1 divided by n plus 1, right?
Yes.
So
yes,
1/2 plus 1 is how much? 3/2, no?
3/2 okay. Thank you. Okay, thank you.
Manideep Sharma.
Good evening, sir.
Good evening.
Sir, am I audible, sir?
Yes, you are audible. Yes.
Sir, go to the today's last problem, sir. ESE 17. I could not see this.
It's coming.
Okay. Sir, you said, sir, normal reaction is passing through the line of action of normal reaction is passing through center, sir. Sir, once
Yes.
explain, sir, how, sir?
Okay. Normal reaction must be perpendicular to the contact surface.
Yes, sir.
That is why it is called as normal.
Yes, sir.
The contact surface is a wall here.
Yes,
Right?
sir. Contact
Wall is tangential to the circle. Right.
Tangential. So, yes. Yeah. Right, sir.
Yeah. So if you draw perpendicular to tangent, it passes through the center. No?
Okay.
Yeah, that is why the normal reaction will pass to the center.
Okay. Good, sir. Thank you, sir.
Yeah. Pranjali Mahajan. Pranjali Mahajan, if you are there.
Hello.
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 I'm audible, sir.
Yes, you are audible. Yeah.
Hello.
Hello. Yes, you are audible. Say it.
Hello.
Hello. You are audible. You are audible.
Hello.
Hello. You are audible. I'm saying again. You are audible. Say your doubt. If you are not able to listen me, just
Hello?
post your doubt. We are able to listen you.
Sir, I'm audible to you.
Yes, you are.
Hello.
Yes. If you can read it, you are audible, Pranjali. Okay. If you are not able to listen to us, post your doubt.
Hello.
Hello, you are audible. You are audible. Am I audible to you?
Sir, I didn't get how you find the location of the first question.
Your question is, how did I find the resultant location? Is that a question?
Yes, sir.
Okay, so see, resultant force will act through the centroid.
Hello.
Hello. Am I audible? Hello. Hopefully I'm audible to you. See, the resultant load will pass through the centroid, so we have to locate the centroid.
Sir, you are not audible to me.
I am not audible. This is class going on from 5:30, and now you are saying I'm not audible to you. How this miss through the class? I should be audible. Yeah, others I must be audible, right? To others I must be audible. Otherwise, you would have killed this Q&A section. What to do now? Then was class audible to you, Pranjali? Miss, how did you hear the class? You send me doubt on the WhatsApp. I will answer there. You send me on the WhatsApp. I will answer there. Okay. I hope you are.
Okay, sir.
Yeah.
Thank you, sir.
Grishma.
Hello.
Hello. Yes.
Yes, sir. Sorry, sir, I could not connect while you are calling.
Okay, no
My
problem. Yes, now ask it.
so my question is on the last question.
This one.
Yes, sir. Here there were not mentioned like it is the cord is stiff or not. Like it's not massless or nothing. The behavior of the string is not mentioned here. So why did we take? It can be in the air also, no, sir. Why did the ball touch the
Wall.
wall? Yeah.
Okay. Now see, string is inclined, right?
Yes, sir.
And if you want to think about the possibility that the ball is not touching the wall, I don't think that can happen because string is inclined. That inclined string cannot balance the vertical weight, right? Because if the ball is not touching the wall, then there will be only two forces: string tension and the weight. Weight is vertical, string is inclined. Two forces can never be in equilibrium if they are not in one line.
I mean, if the cord is stiff, the cord is stiff.
Cord is stiff means, do you want to say it is a rod?
It's like yes, sir.
Yeah, if it is a rod, then you got to weld it there, right? So it is possible in that case, but not with the cord, not with the cord.
I mean, you have said some terms like it can be rod, a thread.
No, I didn't say cord and rod are two different things. Cord means a cable. Cable can take only tension, but rod can take compression also. Rod and cord are two different things.
So cord is like it takes
cord
only
is cable.
Yeah, it takes only axial loads.
It takes only axial tension. Not even compression.
Yes. Axial is like both tension and compression.
Axial is both. Yeah, axial can be tension or compression.
And the other
tension,
doubt is yes,
tension compression both are axial. Yeah.
And the other doubt is the before one.
This one.
ACB. Yeah, yes, sir. Sir, here the RAH, the reaction direction is towards right.
RA is towards right. Okay, what is your doubt?
Sir, why it is not with the other opposite direction? How can we decide this?
Miss towards left, you want to say. Why not towards left?
Yes, in the direction of RBH.
Okay. Now listen this. Whenever you are showing the reaction directions, okay,
yes,
show any direction, right, left, upward, downward, any direction. Okay, and then write the equilibrium equations. You write the equilibrium equations, and equilibrium equations will give you answer. If it is plus answer coming, then whatever direction you assumed is correct. If it is negative answer coming, then whatever direction you assumed is wrong, opposite direction is correct. Is that okay?
Yes, sir.
Okay. So tomorrow I will take a numerical where I will assume the wrong directions and I will show that the negative sign what it means. Okay.
Yes, sir.
Yeah.
In the last doubt, sir, XG. I did not understand XG, sir.
Here in this numerical.
I mean, in the wings aeroplane.
Yeah, it's coming on the screen.
XG. I mean, you explained by taking. Yes, this one, sir. The yellow shaded part towards right.
XG is the X location of the resultant.
Yes, sir. Yes, sir.
So which part you didn't understand?
The 3 steps below the diagrams.
These steps. See yes, the one I'm highlighting. These steps.
Yes, sir.
Okay, now see. See, you have parabolic loading, and you want to replace it by resultant. Okay, so moment must be same, right?
Yes, sir.
So I'm taking the moment. So if I think of the parabolic loading, the load is this. Load is this. See, load load is this y into dx is the load. If I multiply by x, it is the moment.
Yes, sir.
Now this must be equal to the moment of the resultant. Moment of the resultant is resultant into perpendicular distance.
Yes, sir.
So you just do cross
So
multiplication for
M
a.
by R. Yeah. Yes, sir.
Yeah. So
Yes, sir.
so
I got it.
so that's how xc will come.
Thank you so much, sir.
Welcome. Okay, that was the last doubt. Piyush has posted something about doubt. Okay, I have doubt on numerical related aeroplane in which calculating the uplift force. Okay, I want to know only how distance of center is calculated. Okay, Mike is not. Okay, Piyush, if you are there, see, miss, this is a centroid formula. The formula of the centroid is xg is integration area or dA into x divided by integration d. This is the standard formula of calculating any centroid, which we use here. Okay, okay. All the doubts are answered. Okay, so we'll stop here. I hope you had a good session today. Tomorrow will be numerical sessions because we'll solve lots of numericals on the free body diagram. Okay, we'll meet tomorrow at 5:30. Thank you very much. Good night.